Hello there, and welcome to the Cosmographer. Somewhere on this list there is a place on our own moon where the sun has never risen, and where the ground sits at 25 Kelvin, colder than the surface of Pluto. That is number 19. Number 15 is a planet whose atmosphere is made of vaporized rock, driven across the surface at 5,000 kilometers an hour, cooling as it goes and falling as mineral rain onto a frozen nightside. Number 9 is a single dying star that has spent tens of thousands of years drawing a corkscrew across 300 light-years of sky, at a quarter of the speed of light. And number 4 is a sound. One note, B-flat, 57 octaves below middle C, sustained without interruption for 2.5 billion years. Over the next 3 hours, we count down 20 real places in space, none of them the ones everybody names, ranked not by distance or by danger, but by how much of what we assume a place has, each one quietly removes. Get comfortable and settle in. If you enjoy falling asleep to lists like this one, a quiet like and subscribe helps this channel reach more curious minds like you. Because the place at the top of this list is not remote, or hidden, or hard to reach. It has been directly overhead your entire life, and we only worked out what it was 6 years ago. Let's begin at number 20. Number 20, the hollows of Mercury. There are 20 places on this list, and none of them are the ones you would expect. There is no black hole interior here. There is no neutron star surface, no wandering rogue planet, no enormous void with a name everyone already knows. Every entry is a specific location with a catalog number, a discovery date, a set of measured values, and at least one thing about it that nobody has yet explained. Several of them you will not have heard of, and that is deliberate. The list is ordered by a single idea, and it is worth stating plainly before we begin. Each of these places removes something we quietly assume a place has. Light, solid ground, air with enough pressure to hold a liquid, the distinction between weather and geology, the assumption that matter is what a thing is made of, and at the very end, the assumption that we already know what is directly overhead. We start close to home, with a planet that is losing pieces of itself. Mercury is the smallest planet in the solar system and the closest to the Sun. It has been mapped, orbited, and photographed. We have a global image of its surface. And scattered across that surface, mostly on the floors and walls and central peaks of impact craters, are features that do not exist anywhere else in the solar system. They are called hollows. They are shallow, flat-floored depressions with no raised rim, steep walls, and an unusually sharp edge where the wall meets the surrounding terrain. Every one of them is ringed by a halo of bright material that reads as distinctly blue in color imaging, on a planet where almost everything else trends red. They were formally identified and named by David Blewett of the Johns Hopkins University Applied Physics Laboratory and his colleagues in a paper published in Science in 2011 using imaging from the Messenger spacecraft. Messenger had entered orbit around Mercury in March of that same year and would go on operating until 2015. Before it, the only close look anyone had was Mariner 10, which flew past in 1974 and returned images showing unresolved bright patches in craters named Balzac, Tyagaraja, Zeami, and Hopper. Those patches were noted, catalogued, and set aside because the resolution was nowhere near good enough to say what they were. They stayed set aside for 37 years. The type locality, the place where hollows were first properly measured, is the floor of the Radcliffe Basin. Shadow lengths there gave a mean depth of about 44 meters. A much larger survey that Blewett and his colleagues published in 2016 catalogued 2,518 individual hollows across 552 high-resolution images and found a mean depth of 24 meters, plus or minus 16. Their widths run from a few tens of meters up to a few kilometers. So the typical hollow is roughly the depth of an 8-story building and anywhere from the size of a football pitch to the size of a small town. The named craters that host them read like a list of writers and composers, because that is Mercury's naming convention. Radcliffe, Tyagaraja, Dominici, Scarlatti, Warhol, Zeami, Hopper, Eminescu, Lermontov, Dario, Truffaut, Sholem Aleichem. Inside the enormous Caloris Basin, there are more, in craters called Kertész, Sander, Sontag, Nawahi, and Balanchine. In every case, the pattern is the same. The hollows are concentrated where an impact has dug down and exposed material that was previously buried. That pattern is the clue to what is happening. The leading explanation is that some volatile component of Mercury's crust, something that does not stay solid when exposed to the surface environment, is being lost. Sublimation and thermal decomposition, helped along by the solar wind sputtering ions off the surface and by constant micrometeoroid bombardment, remove that component. The rock around it, having lost part of its structure, collapses. The bright halo is what is left behind. Mercury's surface conditions explain why any volatile there is living on borrowed time. The planet turns 3 times for every 2 orbits it completes, a rhythm astronomers call a 3-to-2 spin-orbit resonance, which stretches a single solar day there to about 176 Earth days. Over that long day, the sunlit surface climbs to roughly 700 Kelvin, and over the equally long night, it falls to about 100. That is a 600-degree swing, applied over and over, with no atmosphere to buffer any of it. Anything in the rock that can leave eventually leaves. The prime suspects are sulfides, specifically magnesium sulfide and calcium sulfide. The evidence is an absorption feature near 630 nanometers in messenger color spectra of hollows in Dominici, Hopper, and Radcliffe. That matters because Messenger had already established something unexpected about Mercury as a whole. Its surface is far richer in volatiles than the Moon's, and in particular far richer in sulfur, which is genuinely difficult to explain for a planet that formed as close to the Sun as this one did. Mercury should have been baked clean. It was not. Now for the part that makes hollows worth putting on this list. The strongest evidence that they are young is an absence rather than a presence. Their floors carry no superposed impact craters. None. Meanwhile, the terrain immediately around them is peppered with small craters, exactly as you would expect on a surface that has been sitting in the inner solar system for billions of years, collecting hits. The hollows have not collected any. Their shape supports the same reading. The brinks are sharp. The wall profiles are straight. There is none of the softening and slumping that any landform accumulates over geological time. Blewett's 2016 modeling derived a lateral enlargement rate of roughly 1 centimeter every 70,000 years and proposed that a hollow eventually stops deepening when a layer of volatile depleted material builds up on its floor and shields the rock underneath. After that, it can only grow sideways. The phrasing that appears consistently in the literature is that hollows may be forming today. It is worth being precise about what that claim rests on. It is an inference from morphology and from the absence of craters. Nobody has photographed a hollow at 2 different times and seen it change. There is no before and after detection. What we have is a landform that looks brand new on a planet where nothing else does. Hollows are also distinct from Mercury's volcanic pits, which are deeper, more irregular, gentler sloped, and surrounded by redder material, rather than bluer. The interesting case is Tyagaraja, where a pyroclastic vent and a field of hollows sit side by side, which hints that both may be tapping the same buried volatile source. The next real test is already on its way. Bepi Colombo, a joint mission of the European and Japanese space agencies, launched in 2018 and completed its 9th and final gravity assist on the 8th of January 2025. A thruster problem on its transfer module in April of 2024 pushed orbit insertion back from December of 2025 to the 30th of November 2026, so as this is being recorded, it is still in cruise. When it arrives, its imaging system and its thermal infrared spectrometer should finally identify what the volatile actually is. And with repeat imaging over the course of the mission, there is a real chance of catching a hollow in the act of enlarging, which is the thing to hold on to here. This is the only place we know of where a planet's surface may be visibly dissolving on a timescale a person could care about. Not eroding over epochs. Not weathering under an atmosphere because there is no atmosphere. Simply losing pieces of itself into vacuum in the open while we watch. But the next place on this list is colder than Pluto, and it is on the Moon. Number 19. The permanently shadowed craters of the lunar South Pole. The Moon is the object every human being who has ever lived has looked at. It has been mapped to the meter. 12 people have walked on it. And there are places on it where the sun has never risen. The reason is a single number, and it is a small one. The Moon's axis is tilted about 1.5 degrees relative to the plane of its orbit around the Sun. Earth's tilt is 23.5 degrees, which is why we have seasons and why the poles get months of daylight followed by months of darkness. The Moon has almost none of that. At the lunar poles, the Sun never climbs more than about 1.5 degrees above the horizon. It circles around, low, permanently, which means that any depression deep enough to hide below its own local horizon is in shadow and stays in shadow through every lunar day, every lunar year, and every year after that. The named examples at the South Pole are worth learning because several of them are about to become the most discussed pieces of ground off Earth. Shackleton is 21 kilometers across and 4.2 kilometers deep, centered almost exactly on the pole itself. Shoemaker is about 50 kilometers wide. Faustini is 39. Haworth is 51.4. De Gerlache is 32.4. And Cabeus, the largest of the group, is 98 kilometers across, sitting about 100 kilometers from the pole. Haworth, Shoemaker, and Faustini are old craters with notably flat floors, which is part of why they hold shadow so well. The Diviner instrument aboard NASA's Lunar Reconnaissance Orbiter measured what the temperature is down there. In the coldest of these floors, it recorded values around 25 Kelvin, with one figure reported as low as 23. Kelvin is measured from absolute zero, so 25 Kelvin is 25 degrees above the coldest anything can be. The single coldest spot measured anywhere in the survey was in Hermite Crater near the North Pole at -249 degrees Celsius, about 26 Kelvin. At the time, it was described as the coldest temperature ever measured anywhere in the solar system. Here is the comparison that makes that number land. Pluto's surface averages somewhere around 40 to 44 Kelvin. Pluto is the object we use as shorthand for cold and far away. It sits roughly 5.5 hours of light travel time from here, out past everything. The floors of these lunar craters are colder than Pluto by 15 to 20 degrees. And they are on a world whose light reaches us in a little over a second. The area involved is not trivial either. Using laser altimetry from the same spacecraft, Mazarico and colleagues put the permanently shadowed area poleward of about 80 degrees south at roughly 16,100 square kilometers. Higher resolution reanalysis raised that figure to nearly 21,000. That is a region larger than Wales, on the Moon, that has no light in it. How long has it been dark? The classic figure quoted for decades was 2 billion years or more. That number has recently been revised, and the revision is more interesting than the original. Schorhofer and colleagues showed in 2023 that most of these permanently shadowed regions arose less than 2.2 billion years ago, with an average age of at most about 1.8 billion. Earlier than that, during a transition in how the Moon's spin axis was oriented, its tilt may briefly have reached something like 77 degrees. At that angle, sunlight would have reached every crater floor on the Moon, and any ice already accumulated would have been destroyed. So whatever is down there now started collecting after that. On the 9th of October 2009, NASA found out what is down there by hitting it. The L-Cross mission drove the spent Centaur upper stage of its launch vehicle into Cabeus at high speed, with a shepherding spacecraft following 4 minutes behind, flying through the resulting plume of debris with its instruments running before impacting itself. Anthony Colaprete of NASA Ames led the analysis. The plume contained water at 5.6% by mass, plus or minus 2.9. That is roughly twice as wet as soil from the Sahara. Around 155 kilograms of water vapor and ice were thrown up into view. The plume contained other things as well, and this is where it gets strange. Carbon monoxide, ammonia, methane, hydrogen sulfide, sodium, silver, and mercury, the metal, frozen solid on the floor of a crater on our own Moon. That inventory makes sense once you look at the temperatures again. Water ice is stable against sublimation, below about 110 Kelvin, which is why the Moon holds water at the poles at all. But at 25 to 40 Kelvin, a whole additional class of substances freezes out and stays frozen for geological time. Carbon monoxide, nitrogen, methane, ammonia, elemental mercury. These traps are not just holding water. They are archives, holding whatever comets and the solar wind have delivered, sorted by temperature and preserved. Paul Hayne and colleagues published work in 2021 showing that the shadowing works at every scale, all the way down. They modeled shadows from 1 kilometer across, down to 1 centimeter, 1 centimeter being about the smallest scale at which cold trapping still works. Their total cold trap area across both poles came out at roughly 40,000 square kilometers, more than double previous estimates. And the smallest traps turned out to be by far the most numerous, contributing 10 to 20% of the total area. Ice can hide in a shadow the size of a footprint. An astronaut walking across apparently ordinary regolith could be stepping over thousands of individual cold traps, each one holding material older than complex life on Earth. Now, stand on the rim of Shackleton Crater and look down. You are in sunlight. The sun sits 1.5 degrees above the horizon behind you, and it does not rise any further, because there is no further. It circles the horizon slowly, holding that same angle. Your shadow runs out ahead of you for kilometers across the regolith, and its edge is perfectly sharp, because there is no air to soften it. The rim you are standing on is one of the best lit places on the Moon. Shackleton's rim peaks catch sunlight for 80 to 90% of every lunar orbit, which is precisely why every landing plan wants to put hardware here. A few meters in front of you, the ground begins to fall away. You follow it with your eyes, and somewhere on that slope, there is a line where the low sunlight stops. Below that line, the floor is 4 kilometers down, and it is not dark the way a night is dark. starlight reaches it. The surrounding rim glows faintly. But no photon from the sun has landed there in something like 1.5 billion years, and across that boundary, over a drop you could walk in an afternoon, the temperature falls by 200 Kelvin. The frost on that floor is older than every multicellular organism that has ever lived on Earth. It has been sitting there, undisturbed, through the entire history of animal life on the planet, hanging in the sky above it. Artemis II flew from the 1st to the 10th of April 2026, carrying Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen around the Moon at an altitude of 6,545 kilometers, and setting a human distance record of 252,756 miles. Artemis III, the crewed landing at the South Pole, is currently targeted for late 2027. The Viper rover, cancelled in 2024 and revived in 2025, is assigned to a lander due at the South Pole the same year. Within a few years, someone is going to stand at the edge of one of these and look in. The next place has enough air that water could sit in an open cup, and it would still kill you in under a minute. Number 18. Hellas Planitia. Mars has a lowest point, and it is not a canyon. It is a hole punched into the southern hemisphere by something roughly 370 kilometers across, somewhere between 4.1 and 3.8 billion years ago, during the era when the inner solar system was still being bombarded by leftover material. The hole is called Hellas Planitia, and it is the 4th or 5th largest confirmed impact structure in the solar system. The floor lies about 7,152 meters below the Martian datum, which is the reference level Mars uses in place of a sea level it does not have. The basin spans roughly 2,300 kilometers from east to west, centered near 42 degrees south and 70 degrees east. But the number that gives the best sense of it is the rim-to-floor relief, which exceeds 9,000 meters. You could set Mount Everest, all 8,849 meters of it, on the floor of Hellas, and the summit would still be below the rim. You would stand on top of the highest mountain on Earth and be looking up at the edge. For comparison, Hellas is about 3,000 meters deeper than the South Pole Aitken Basin on the Moon, which is the largest confirmed impact structure anywhere in the solar system. And yet Hellas has notably modest rim peaks for its size. Head and Palumbo proposed an explanation in 2018 that is worth pausing on. An impact of that scale would have vaporized enough rock and ice to produce global hot rainfall and meltwater flows, and those flows would have eroded the basin's own rim while it was still forming. The crater partly washed away its own edges. What makes Hellas genuinely unusual, though, is the air. Atmospheric pressure increases as you descend, on Mars exactly as on Earth, because there is more atmosphere stacked above you. Mars Global Surveyor Radio Science measured about 11.5 millibars on the floor of Hellas, which is 1,150 pascals, and winter values, when the air is densest, have been cited as high as 12.4 millibars, or 1,240 pascals. The Martian reference pressure at datum is 610 pascals. So the floor of Hellas runs at roughly double the planetary average. Now hold that number against another one. The triple point of water sits at 611.657 pascals. The triple point is the pressure below which liquid water simply cannot exist. Below it, ice does not melt. It sublimates directly into vapor, skipping the liquid phase entirely. That is what happens almost everywhere on Mars. Put an ice cube on the surface at datum pressure, and it does not puddle, it evaporates. The floor of Hellas is comfortably above the triple point. Liquid water is thermodynamically permitted there. An open cup of water on the floor of Hellas would not boil away on contact with the air. Pressure, in that one place on that entire planet, is not the limiting factor. temperature is, and the temperature is far too low most of the time, and there is no liquid water sitting there now. But the pressure barrier, the one that rules out the rest of the surface outright, does not apply. It is worth being clear about what that does and does not mean. Hellas is not habitable. The air is carbon dioxide at about 1% of Earth's sea level pressure, which is well below the Armstrong limit, the pressure at which the water in your own tissues begins to boil at body temperature. An unprotected human on the floor of Hellas would lose consciousness in seconds and die in under a minute. It is simply the one location on Mars where the specific failure mode would not be the water instantly leaving. Hellas is also a weather engine. It is a known source region for global dust storms, the planet-encircling events that can obscure the entire surface for weeks. Local storms typically start there in southern summer, when sunlight is strongest and atmospheric convection is most vigorous. The context camera on the Mars Reconnaissance Orbiter imaged a well-defined storm developing inside the basin in July of 2012. Moore and Edgett characterized Hellas back in 1993 as a site of net dust erosion, which is an important distinction. A basin that deep might be expected to fill with dust over billions of years. It does not. It exports material. Hellas is a pump, not a sink. The eastern rim holds ice, and we know because we looked underneath. The Charade radar sounder aboard the Mars Reconnaissance Orbiter can see through several hundred meters of rock and dust. Pointed at 3 craters on the eastern side of Hellas, it found that features previously catalogued as lobate debris aprons, which look like ordinary rocky slope deposits from orbit, are in fact glaciers of water ice buried under a protective layer of debris. The measured thicknesses came out at roughly 250 meters in the upper crater, 300 in the middle one, and 450 in the lower. Bruff and colleagues mapped the region more broadly in 2015, cataloguing what are called viscous flow features across eastern Hellas. These carry the fingerprints of ice that has flowed, convex upward profiles, lineations running parallel to the direction of flow, ridge and trough surface textures. Their conclusion was that the region records at least 2, and possibly 3, separate phases of glaciation. Mars's axial tilt varies chaotically over millions of years, swinging between roughly 0 and 60 degrees, and each swing redistributes the planet's ice. Eastern Hellas has been glaciated, deglaciated, and glaciated again. 2 other features on the floor have no clean explanation at all. In the northwest, there is what has been named honeycomb terrain, a pattern of roughly polygonal cells that may be salt or ice diapirs, columns of lower density material rising slowly through denser material above, driven by a buried ice layer somewhere between 100 meters and a kilometer thick. And on the floor itself, there is a twisted, banded texture that has been informally described as looking like pulled taffy. Nobody has satisfactorily explained either one. There is one more oddity, and it may be a coincidence, or it may not. Hellas Planitia is very nearly antipodal to Alba Mons, the enormous low-relief volcano on the other side of Mars, a relationship first noted by Peterson in 1978. Hellas and Isidis together sit roughly antipodal to the whole Tharsis bulge. Argyre is roughly antipodal to Elysium. The pattern is suggestive, an impact that large sends seismic energy through the entire planet, and that energy converges again at the point exactly opposite. Whether that convergence cracked the crust and triggered the volcanism, or whether these are simply 4 coincidences in a row, has never been settled. While we are on Mars, there is a smaller thing worth mentioning, because it belongs to the same category of places we cannot see into. On the northern flank of Arsia Mons, the Themis instrument on Mars Odyssey identified 7 candidate cave skylights, reported by Glenn Cushing in 2007 and informally named Dina, Chloe, Wendy, Annie, Abby, Nikki, and Jean. They are between 100 and 225 meters across, with minimum depths of 68 to 130 meters. Annie's floor lies at least 130 meters down. In visible images, they are pure black. Their thermal behavior, staying warmer at night and cooler by day than the ground around them, is the signature of open shafts into subsurface voids rather than shallow bowls. Nobody has seen the bottom of any of them. The next entry is only 6.5 light-years away, and its weather is made of iron. Number 17, Luhman 16b. In 2013, Kevin Luhman of Pennsylvania State University found something in data from NASA's Wide Field Infrared Survey Explorer that should have been found decades earlier. It is a pair of brown dwarfs, catalogued as WISE J10491557-531906.1 and known to everyone as Luhman 16. It lies 6.51 light-years away in the constellation Vela. That distance makes it the third nearest stellar system to the Sun, after Alpha Centauri and Barnard's star. It is the nearest pair of brown dwarfs known. And it went unnoticed until 2013 for a mundane reason. It sits projected against the crowded plane of our own galaxy, one faint object among an enormous number of others, hidden in the traffic. There is a further detail that reframes it. Luhman 16 is only about 3.5 light-years from the Alpha Centauri system. It is closer to Alpha Centauri than we are. If you were standing on a hypothetical world at Alpha Centauri and someone asked you to name your nearest neighbor, the answer would not be the Sun. Brown dwarfs occupy an awkward category. They are too massive to be planets and too light to sustain the hydrogen fusion that makes a star a star. They form the way stars form, by collapsing out of a cloud, but they never ignite properly. What they emit is leftover heat from their own formation, and they spend the rest of cosmic history radiating it away and going slowly dark. There is no long, stable phase. There is only cooling. Luhman 16a is spectral type L7.5, with a mass of about 35 times Jupiter's. Luhman 16b is type T0.5, at about 29 Jupiter masses. Both have effective temperatures near 1300 Kelvin. B rotates once every 5.28 hours. The two orbit each other every 26.5 years at a mean separation of 3.52 astronomical units, which is roughly the distance from the Sun to the asteroid belt. The reason astronomers wanted a close look at this particular pair is that it straddles a boundary. The transition from spectral type L to spectral type T is where something happens to the atmospheres of these objects. The condensate clouds in their visible layers break up, and their carbon chemistry shifts from carbon monoxide toward methane. Nobody had ever watched that boundary from close range, because nothing that close had been found. On the 5th of May 2013, Ian Crossfield and colleagues observed the system for 5 hours using the Cryer spectrograph on the European Southern Observatory's Very Large Telescope. 5 hours is one full rotation of the B component. The technique they used is called Doppler imaging, and it works on a principle that is elegant once you see it. As an object rotates, the side turning toward you is blue shifted, and the side turning away is red shifted. Any feature on the surface therefore leaves its fingerprint at a specific position within the shape of a spectral line, and that position sweeps across the line as the feature rotates around. Track that over a full rotation, and you can reconstruct a map of an object you cannot resolve at all. The result appeared in Nature in January of 2014. It was the first surface map ever made of a brown dwarf. What it showed was a large dark region at mid-latitudes, a brighter patch near the opposite pole, and mottling around the equator. The reading is patchy global cloud decks, where dark means thick cloud and bright means a gap letting light out from the hot interior below. Then they looked again, and the map had changed. It evolves on roughly a one-day timescale. This is weather, in the ordinary sense of the word, on an object 6.5 light-years away, and it is different tomorrow. Luhman 16b is among the most photometrically variable brown dwarfs known, sometimes exceeding 20% in amplitude. 20% means the total brightness of the entire object rises and falls by a fifth as it turns, purely because of what is passing across the face. Only one known brown dwarf is more variable. There is also a timing element worth noting. Luhman 16 is receding from us at about 21.5 kilometers per second. It made its closest approach roughly 36,000 years ago, when it passed within about 5 light-years. Human beings were alive and painting on cave walls, while the nearest brown dwarfs to the sun were as close as they will ever get, and nobody looked up and noticed, because there is nothing there to see without an infrared telescope. The rotation itself turned out to be more complicated than a single number. Apai and colleagues used photometry from the TESS spacecraft in 2021 to refine B's period to 5.28 hours, and in doing so, found evidence of differential rotation, with bands at different latitudes turning at measurably different rates. That is exactly what Jupiter does, and exactly what the Sun does. It means the atmosphere is not being carried around rigidly by the body underneath it. It has its own circulation. Hubble had already contributed to the picture. Time-resolved spectroscopy, taken between 2014 and 2016, produced maps of the cloud structure in both components at multiple epochs, and the structures had reorganized between them. Between the Doppler map, the Hubble maps, and the later Space Telescope work, there is now more than a decade of weather observation for an object no telescope can resolve as anything but a point of light. Now to what those clouds are made of. At around 1300 Kelvin, at the pressures found in these atmospheres, iron and silicate minerals such as enstatite and forsterite are above their condensation temperatures. They are gases. As they circulate and cool, they condense. The phrase that gets used is iron rain, and it is worth being precise about it, because it is literally true and also not quite what the words suggest. There is no surface for anything to land on. A brown dwarf has no ground. It is gas all the way down, growing steadily denser until it becomes something with no terrestrial analog. What happens is that gaseous iron condenses into liquid or solid droplets. Those droplets are denser than the surrounding hydrogen, and so they settle downward under gravity, out of the layers we can see. Atmospheric chemists call the process rain out. It is not a downpour onto a landscape. It is metal condensing out of a sky and sinking permanently, taking the iron with it. In 2025, a 70-day spectroscopic campaign using Gemini South tried to detect iron hydride in both components and failed. That failure is informative. It implies iron is being removed from the visible atmosphere more efficiently than the models predict. The same campaign did detect water, carbon monoxide, hydrogen, hydrogen sulfide, hydrogen fluoride, and, newly, ammonia in both objects. For a while, there was a third member of the system. Boffin and colleagues reported in 2014 that the orbital motion of A and B showed perturbations consistent with an unseen body of somewhere between a few and 30 Jupiter masses. That claim has been steadily dismantled ever since. Salmon and Lazarenko excluded anything above 2 Jupiter masses in 2015. Bedin and colleagues ruled out Neptune mass objects at 1 to 2 year periods in 2017 and tightened the constraint again in 2024. The Gemini radial velocity campaign found nothing. 8 hours of JAWS time were spent watching for transiting moons, sensitive down to bodies smaller than our own moon. Nothing there either. UST did look at the pair properly in 2024, with 8 hours of mid-infrared observation followed by 7 hours in the near-infrared. Water, carbon monoxide and methane in both. And in component A, a flat plateau in the spectrum beyond 8.5 microns, which is the signature of fine-grained silicate cloud sitting high in the atmosphere. B does not show it. Neither simple patchy cloud models nor full circulation models could reproduce the light curves the telescope actually recorded, which is where this entry lands. The third closest system to our own is a place where the clouds are made of rock and metal. The weather reorganizes overnight, and after 12 years of increasingly sophisticated observation, the models still cannot predict what it will do next. The next place on this list has no atmosphere at all, and a year there lasts less than a work shift. Number 16, GJ367b. On the 2nd of December 2021, a paper appeared in Science describing a planet with a year that lasts 7.7 hours. It was found by NASA's Transiting Exoplanet Survey satellite, and the paper was led by Christine Lamb of the German Aerospace Center's Institute of Planetary Research in Berlin. The host star, GJ367, is a bright red dwarf about 30 light-years away. The planet, GJ367b, completes an orbit in 0.3219 days, 7.7 hours. A year there is shorter than a night's sleep. It has completed more than 3 orbits in the time it takes Earth to turn once, and since the planet formed, it has gone around its star well over 1 trillion times. Because it sits that close, it is almost certainly tidally locked, with one hemisphere permanently facing the star and the other permanently facing away. It is worth saying what a planet like this is doing there at all. Ultra-short period planets, defined as those completing an orbit in less than a day, are rare. Only a small percentage of stars have one. They almost certainly did not form where we find them, because the inner region of a young planet-forming disk is too hot and too sparse to build a planet in place. They arrive. Something moves them inward, and then they sit there, receiving, in this case, roughly 500 times the sunlight that falls on Earth for the rest of the star's life. The discovery numbers gave a radius of about 0.72 Earth radii and a mass of about 0.55. Those were refined in 2023 by Goffo and colleagues, using 371 radial velocity measurements from the HARP spectrograph collected over roughly 3 years, combined with 2 sectors of TESS photometry. The refined mass is 0.633 Earth masses to 8% precision. The refined radius is 0.699 Earth radii to 3.4%. The instrument that made the mass measurement possible deserves a mention, because the measurement is genuinely difficult. HARPS is the high-accuracy radial velocity planet searcher, mounted at the European Southern Observatory's La Silla site in Chile, and it detects planets by measuring how much a star wobbles as an unseen companion pulls it around. For a body 2/3 the mass of Earth, that wobble is well under a meter per second. HARPS was measuring a star 30 light-years away, moving at roughly walking pace, and doing it consistently enough, over 3 years, to pin the planet's mass to 8%. Put those together and you get a bulk density of 10.2 grams per cubic centimeter, plus or minus 1.3. Earth's bulk density is 5.51. So GJ367b is 85% denser than Earth, while being noticeably smaller than Earth. That combination is not something you can arrange with ordinary rock. There is really only one way to read it. The inferred iron core mass fraction is 0.91. Roughly 9/10 of that planet, by mass, is iron. It is the densest small, ultra-short period planet known, and it belongs to a rare class informally called super-Mercuries, bodies that are essentially bare planetary cores. How a planet ends up that way is unresolved, and the candidate explanations are all violent or slow. A giant impact may have stripped away the silicate mantle and left the core. Or the star may have evaporated the mantle off over time. Or the planet formed in a region of its disk that was already enriched in iron. Nobody knows which. The equilibrium temperature works out to about 1,365 Kelvin. But in February of 2024, Zhang and colleagues published something better than a calculation. They used JUST's mid-infrared instrument to take a thermal phase curve, watching the planet across 5 to 12 microns through a full orbit, measuring how much heat comes off it and from where. The eclipse depth came in at 79 parts per million. That gives a measured dayside temperature of 1,730 Kelvin, hotter than the equilibrium calculation, which tells you the surface reflects essentially nothing and absorbs almost every photon that lands on it. The night side came out below 850 Kelvin, and the relative phase amplitude was 0.97 plus or minus 0.10. That last number is the important one, and it is worth unpacking. Phase amplitude measures how much heat gets carried from the day side to the night side. On a planet with an atmosphere, winds move warmth around, the night side is warmer than it should be, and the amplitude is reduced. An amplitude of 0.97 means essentially none of the heat crosses over. There is nothing to carry it. So GJ367b has no atmosphere. None. The day side is molten and black. The night side is simply cold. And the terminator, the line between them, is not a gradient. It is a boundary you could step across, with roughly 900 Kelvin of difference on either side of your feet. For scale, hold it against Mercury, which is the solar system's own attempt at this. Mercury takes 88 days to orbit. It is about 70% iron by mass. Its bulk density is 5.43. Its dayside peaks near 700 Kelvin. GJ367b orbits roughly 275 times faster, is about 91% iron, is nearly twice as dense, and runs about 2.5 times hotter. It is Mercury's premise taken to its structural limit. The same 2023 analysis that refined the planet's mass also found two siblings hiding in the data. GJ367c has a period of about 11.5 days and a minimum mass of about 4 Earth masses. GJ367d has a period of about 34 days and a minimum mass of about 6. Neither transits, so their sizes are unknown. What is interesting is that the two of them sit close to a 3-to-1 relationship in their orbital periods, which is the kind of arrangement that tends to arise when planets migrate inward and lock into resonance with each other. It is a hint, not a proof, about how the innermost one ended up on a 7-hour orbit. One last thing about the host star. Red dwarfs like GJ367 burn their fuel with extraordinary parsimony, and their main sequence lifetimes run into the hundreds of billions of years. Long after the Sun has swollen, shed its outer layers and settled into a slowly cooling white dwarf, this star will still be shining, and this ball of iron will still be going round it, 3 times a day, indefinitely. The next world does have an atmosphere. It is made of vaporized rock, and it rains. Number 15, K2-141b. K2-141b was found by transit in 2018 during the extended mission of the Kepler Space Telescope and described in two near-simultaneous papers, one led by Malavolta and colleagues and one by Barragan, Gandolfi and Dye. Its mass came from the HARPS North spectrograph. The host is an orange dwarf star about 200 light-years away. A word about how it was found, because the circumstances were unusual. Kepler was designed to stare at a single patch of sky for years, and it did that until 2 of its 4 reaction wheels failed, and it could no longer hold its aim. Rather than abandon it, engineers worked out that the pressure of sunlight itself could act as a third stabilizer, balancing the spacecraft against the photons falling on it. The resulting extended mission, called K2, ran from 2014 to 2018, pointed along the ecliptic, and found this planet among many others. A telescope steadied by sunlight found a planet being destroyed by it. The orbital period is 6.73 hours, at a distance of about 1.07 million kilometers from the star. For comparison, Mercury sits 58 million kilometers from the Sun. This planet is more than 50 times closer to its star than Mercury is to ours, orbiting a star that is smaller and cooler than the Sun, but not nearly cool enough to make that survivable. It has a radius of 1.51 Earth radii and a mass of 5.08 Earth masses, giving a density of 8.2 grams per cubic centimeter and implying an iron core making up 30 to 50% of the total. So it is a rocky planet, half again as wide as Earth, 5 times as heavy, and it is being held about 1 million kilometers from a fire. It is tidally locked, but the geometry produces something you would not immediately expect. Because the star is so close, it is enormous in the planet's sky, and a star that large does not illuminate exactly half the planet. It wraps around. Roughly 2/3 of the surface is in perpetual daylight. That leaves about 1/3 in permanent night, and the boundary between them is not on the equator of the day-night geometry you would draw for a distant star. It is pushed well around toward the far side. The equilibrium temperature is 2039 Kelvin. The modeled day side reaches about 3270 Kelvin. That is not merely hot enough to melt rock. It is hot enough to boil it. The permanent night side sits below 73 Kelvin. In November of 2020, a team including the graduate student Jiang Nguyen at York University and Nicholas Cowan at McGill published a full climate model of the planet. Their conclusion is that the day side is covered by a magma ocean about 100 kilometers deep. For scale, the deepest trench in Earth's oceans is a little under 11 kilometers. This is an ocean of molten rock, roughly 11 times deeper than that, covering 2/3 of a planet. Above the magma ocean, there is an atmosphere. It is not made of gas in the ordinary sense. It is made of the ocean. At 3200 Kelvin, rock does not just melt, it evaporates, and the atmosphere of K2-141b is composed of sodium, silicon monoxide, and silicon dioxide in vapor form. Silicon monoxide is a molecule almost never encountered in terrestrial chemistry because it is unstable at Earth conditions. There, it is a normal constituent of the air. Sodium is worth singling out because it is the reason we can hope to test any of this. Sodium has an extremely strong pair of spectral lines in the yellow part of the spectrum, the same lines that give sodium street lamps their color. If a planet has sodium vapor in its atmosphere, that signature is one of the easier things to look for from a distance. Rock vapor atmospheres are, in that narrow sense, cooperative. They announce themselves. Vaporized rock behaves like any other atmosphere. It has pressure gradients, and pressure gradients produce wind. The modeled winds exceed 5,000 kilometers per hour. Some analyses give figures above 6,000. Every one of them is comfortably supersonic. There is a wind of vaporized rock moving faster than sound across an ocean of lava. And that wind goes somewhere. It carries the rock vapor off the day side and out over the terminator into the third of the planet that never sees the star. There the temperature falls below 73 Kelvin. The vapor cools. It condenses. And it falls. Stand on the night side and look up. There is nothing to see. The star has never risen here and never will. The sky holds whatever stars are visible from 200 light-years away in that direction, and the ground beneath you is colder than the surface of any world in our solar system except the outermost. The temperature is below 73 Kelvin, which means that not only water, but almost every volatile substance that has ever existed on this planet is frozen solid and has been for as long as the planet has been where it is. And out of that dark, quietly, comes a steady fall of mineral. It arrives from a direction, carried in on a wind you can measure but that carries almost no substance, because the atmosphere here is thin and getting thinner as it condenses out. Silicon and sodium, vaporized a third of a world away, on a surface that this hemisphere will never see, are settling onto the frozen ground. Not as a storm. As a slow, permanent, one-directional accumulation, grain by grain, the way snow settles in still air. The material falling on you was liquid rock an hour ago. Then the magma currents underneath carry it slowly back. That is the cycle: vapor out, mineral down, then a sluggish return flow through the molten interior, back toward the hot side, to be evaporated again. Here is the part the modeling team drew attention to, and it is the reason this planet matters more than it would as a curiosity. The return flow is far slower than the atmospheric transport. The cycle does not balance. Material is being moved from the day side to the night side, faster than it is coming back. Which means the composition of the planet is changing. The surface is changing. The atmosphere is changing. This is not a stable climate on a fixed world. It is a climate that is slowly rewriting the planet it belongs to, and it has been doing so since the planet arrived at that orbit. K2-141b was for a while the shortest period planet with a precisely determined mass, which is why it became the standard test case for modeling worlds like this, rather than remaining an oddity in a catalogue. And that has a consequence worth stating plainly. The magma ocean is not a colorful hypothesis bolted on to make the object interesting. It is the only stable configuration available. Any rocky planet placed at that distance from that star would end up looking like this. Put Earth there, and within a geological instant, it would have a magma ocean, a rock vapor atmosphere, supersonic winds, and mineral snow on its dark side. That generality is what makes it useful to astronomers, and it is also what makes it worth putting on a list like this one. It is not a freak. It is a category. There are more of these than there are of us. Similar worlds are already known. Corot-7b, Kepler-10b, 55 Cancri. Together they form a small class of ultra-short-period rocky planets that are all thought to carry magma oceans, all thought to have rock vapor atmospheres, and all thought to be doing some version of this right now. The next entry does all of this too, but only for 30 hours, every 111 days. Number 14, HD 80606b. On the 4th of April 2001, the Geneva Extrasolar Planet Search announced a discovery in a paper whose title said, "The Important Thing Without Decoration, a Planet on an Extremely Elongated Orbit." The team was led by Dominique Naif, using the LED spectrograph on the 1.93-meter telescope at Haute-Provence Observatory in southern France. The radial velocity variation had actually been noticed 2 years earlier, in 1999, with the Keck 1 telescope in Hawaii. It took a while to believe. The star is HD 80606 in Ursa Major, about 217 light-years away. It has a near-twin companion, HD 80607, sitting about 1,200 astronomical units away, which is roughly 125 times Saturn's distance from the Sun. Keep that companion in mind. It turns out to be responsible for everything that follows. The planet has an orbital eccentricity of 0.93183. Eccentricity measures how far an orbit departs from a circle. 0 is a perfect circle. Earth's is 0.017, which is why our distance from the Sun barely changes across a year. Halley's Comet is about 0.97. HD 80606b is a gas giant of 4.16 Jupiter masses on an orbit that is very nearly a comet's. Here is what that means in distances. The orbital period is 111.4 days. At its farthest point, the planet sits 0.889 astronomical units from the star, about 133 million kilometers. That is a little inside Earth's distance from the Sun. It is a perfectly ordinary place for a gas giant to be, cool and unremarkable, and the planet spends most of its year out there. Then it falls. At closest approach, it comes to 0.0314 astronomical units, 4.69 million kilometers. That is roughly 13 times closer than Mercury's average distance from the Sun, and it puts the planet less than 4 stellar diameters from the surface of the star. Over about 30 hours around that closest approach, the amount of light falling on the planet increases by a factor of roughly 800, and then falls away again. 800 times. Not 8%. Not 8 times. A whole planet, 4 times the mass of Jupiter, has the light on it, multiplied by 800 over the course of a day and a bit, and then has it taken away again, and this happens every 111 days without variation. The planet's density is worth a moment as well, because it is unusual for its class. It comes out at about 5.06 grams per cubic centimeter, which for a gas giant is high. Jupiter's is 1.33. Saturn's is low enough that the planet would float in water. A gas giant with a density comparable to rock is telling you that a large fraction of its mass is concentrated in a heavy element core, and that the object is more compact than its 4 Jupiter masses would suggest. This is a dense, hard object being thrown around a violent orbit, not a puffed-up envelope of hydrogen. In 2007, Greg Laughlin, then at Lick Observatory, and Drake Deming at NASA Goddard, decided to watch it happen. They pointed the Spitzer Space Telescope at the periastron passage of the 20th of November, observing at 8 microns across a 30-hour window that started 20 hours before closest approach and ran until 10 hours after. Their results were published in Nature in January of 2009. The measured brightness temperature climbed from about 800 Kelvin to about 1500 Kelvin in 6 hours. 700 Kelvin in 6 hours across the visible face of a planet. The derived radiative timescale is roughly 4.5 hours at the depth Spitzer was probing, which tells you why the response is so fast. The energy is being dumped into a thin layer high in the atmosphere that has nowhere to put it and cannot shed it quickly enough. It is worth saying why 8 microns was the wavelength chosen, because the choice is not arbitrary. Different wavelengths probe different depths in an atmosphere. Look at one wavelength and you are seeing a layer where the gas takes weeks to respond to a change in heating. Look at another, and you are seeing a layer that responds in hours. Laughlin and Deming picked the channel that would show them something within the length of an observing window, and the gamble paid off. Had they chosen a wavelength probing deeper, they would have watched 30 hours of almost nothing. Laughlin's own description was that they had watched the development of one of the fiercest storms in the galaxy, and that it was the first time weather changes had been detected in real time on a planet outside the solar system. The modeled response is a set of shockwave storms rippling outward from the substellar point at something like 5 kilometers per second, which is around 11,000 miles per hour, with heating on the order of 550 Kelvin developing over a few hours. Ride along for those 30 hours. You begin in the cold. The star is a bright point, brighter than any star in Earth's sky, but still a point, and the atmosphere around you is dark and settled, having spent the last 3 months cooling down from the previous encounter. Then, the point begins to grow. It grows slowly at first, and then not slowly at all. Over the course of a day, it swells from a point into a disk, and the disk keeps swelling, and the light keeps climbing, and there is no cloud layer thick enough to matter. The temperature of the layer you are in goes from 800 Kelvin to 1500 in 6 hours, and the whole face of the planet turned toward the star begins to move. What comes off the substellar point is not a wind in the sense of something blowing past. It is a front. Heated gas expands, and the expansion propagates outward from the hottest point at roughly 5 kilometers a second, spreading across the curve of the planet as a shockwave with a visible edge. Behind it, the atmosphere is a different temperature than it was in front of it. The whole hemisphere is restructured in a matter of hours. And then the star begins to shrink. The planet is already moving away. Within a day, the disk has contracted back toward a point, the light has fallen by a factor of 800, and the atmosphere begins the slow work of radiating away everything it just absorbed. Over the following weeks, it cools back down toward baseline. Then it does it again. The obvious question is how a planet gets an orbit like that, and the answer is the companion star. The mechanism is called the Kozai effect, worked out in the 1960s for asteroids being perturbed by Jupiter long before anyone had found a planet outside the solar system. A distant third body, over long timescales, can trade a planet's orbital inclination against its eccentricity, gradually pumping a nearly circular orbit into an extreme ellipse. The evidence for that reading came in 2009, when Pont and Mutu and their respective colleagues measured the angle between the planet's orbit and the star's rotation. The technique is called the Rossiter-McLaughlin effect, and it works by watching which part of the star's spinning disk the planet covers as it crosses. The measured misalignment is 42 degrees, plus or minus 8. So the orbit is not just stretched, it is tilted at a substantial angle to the star's equator, which is what you expect if something dragged the planet into that orbit rather than it forming there. There is a coda to this, and it is one of the more agreeable stories in modern astronomy. The detection of the secondary eclipse implied only about a 15% chance that the planet would also transit, passing directly in front of the star from our viewpoint. That is not good odds, and transits of a 111-day planet are rare events that last a long time and are easy to miss. It was caught anyway, on the 14th of February, 2009, by Fosse, Waldman, and Kipping, using a 35-centimeter Schmidt-Cassegrain telescope at the University College London Observatory. A 35-centimeter telescope in a European city under city skies caught a transit that the professional facilities had not. Mutu and colleagues confirmed it photometrically and spectroscopically shortly afterward. The transit lasts about 12 hours. Until the Kepler data release of February 2011, HD 80606b held the longest orbital period of any transiting planet known. There is one more reason this system stayed in the literature rather than becoming a footnote. Pearson and colleagues published refined orbital timing work in 2022 for the specific purpose of making the planet observable by UST. Predicting a periastron passage to within a few minutes, more than a decade after the Spitzer observation, requires a very precise ephemeris, and UST's sensitivity would allow something Spitzer could not manage, a genuine temperature map of the heating event, resolved in wavelength and therefore in depth. The storm has been watched once. The plan is to watch it properly. One final detail, because it changes the picture. The planet is not tidally locked. Its rotation and its orbit are not synchronized, which means the face that gets heated at periastron subsequently rotates around, carrying the hot spot into and out of our view. NASA quoted a rotation period of 34 hours in 2009. DeWitt and colleagues measured 93 hours in 2016 against a predicted value of 40. The disagreement is unresolved, and it matters because it governs how the heat gets distributed after the encounter ends. What is not in doubt is the schedule. Every 111 days, an entire planet is thrown at its star, catches fire across its whole day side in 6 hours, and is flung back out to cool. It has been doing that without variation since long before anything on Earth had a spine. The next place on this list was photographed, celebrated, and named. And then it stopped existing. Number 13, Fomalhaut b, the planet that stopped existing. Fomalhaut is one of the brightest stars in the southern sky. People have been looking at it and naming it for thousands of years. It sits 25 light-years away in Piscis Austrinus, about twice the mass of the Sun and about 20 times as luminous. In 2005, Paul Callas, James Graham, and Mark Clampin resolved something around it, a ring of debris, eccentric, and with an inner edge so sharp that the popular press started calling the whole thing the Eye of Sauron. That sharpness was the interesting part. Debris rings do not naturally have knife edges. Left alone, they spread. A sharp inner boundary implies something is holding it there, sweeping the inside clean, the way the moons of Saturn maintain the gaps in its rings. The obvious candidate was an unseen planet. On the 13th of November, 2008, NASA released a Hubble image showing it. Callas, Graham, and their collaborators had identified a moving point source in images taken by Hubble's Advanced Camera for Surveys in 2004 and 2006, at visible wavelengths. Not an inferred wobble in a star's motion, not a dip in a light curve. A point of light in an image that moved between epochs in the way an orbiting body should. It was announced as the first extrasolar planet ever directly detected in ordinary visible light. Callas said at the time that it was a profound and overwhelming experience to lay eyes on a planet never before seen. The image went everywhere. In December of 2015, the object was formally named Dagon, chosen by public vote in the International Astronomical Union's naming campaign. Then the problems started, one at a time. The first was brightness. The object was too bright in visible light for a planet of the mass implied by the ring's structure. Something was adding light. The usual patch was circumplanetary dust, a disk or a cloud of material around the planet, scattering starlight back at us. The second was the infrared. A young giant planet should glow in the infrared with its own formation heat, and that glow should be far easier to detect than reflected visible light. It was not there. Ground-based observations capped the object below 3 Jupiter masses. Then a non-detection by the Spitzer Space Telescope, published by Janssen and colleagues in 2012, pushed the limit below Jupiter's mass entirely. There was a bright point in the visible, and nothing at all where the planet's own heat should have been. The third problem was the orbit, and it was the worst. Hubble data from 2010 and 2012 gave an orbital eccentricity around 0.8 on a path whose projected track crossed the plane of the debris ring. A planet on that orbit could not possibly be the object maintaining the ring's sharp edge. It would plow through it. It would destroy the very feature that had motivated the search. The press began calling it the zombie planet. In April of 2020, András Gaspar and George Rika of the Steward Observatory at the University of Arizona published the resolution. Using Hubble spectrograph data from 2013 and 2014, together with the full archive, they measured what the object had actually been doing across the years of observation. It had been fading, continuously, and it had been expanding, spreading out year on year. By 2014, it had vanished from Hubble images altogether. And when they fitted its motion properly, the path was not an ellipse. It was hyperbolic, an escape trajectory consistent with dust grains around 1 micron across being pushed outward by the pressure of the star's own light. Radiation pressure is the mechanism, and it is worth explaining because it is the reason the object could vanish. Light carries momentum. When a photon strikes a dust grain, it gives that grain a small push outward, away from the star. For large particles, the push is negligible against gravity. For very small ones, the grain is dragged along with the surrounding gas. But in a narrow size range around a micron, the outward push wins, and those grains are expelled from the system entirely. A collision between two large bodies produces debris across every size, but only that narrow band gets flung outward as a visible, expanding, fading cloud. Which is precisely what the measurements showed. Their conclusion was that Fomalhaut B was never a planet at all. It was the expanding debris cloud from a catastrophic collision between two planetesimals, each roughly 200 kilometers across. They estimated that an event of that size happens in that system about once every 200,000 years. The cloud is now larger than the orbit of Earth and has faded below Hubble's detection threshold entirely. On the 7th of May 2020, the NASA Exoplanet Archive removed Fomalhaut B from its catalogue. There had been warnings in the sense that alternatives existed. Bowley and colleagues showed with ALMA data in 2012 that smaller, unseen planets could shape the ring's sharp edge perfectly well without needing Fomalhaut B to be involved at all. Gallagher, Marois and colleagues proposed an earlier version of the collision idea in 2013 involving two objects of about 50 kilometers radius colliding within the previous century. The pieces of the answer were on the table for years. What was missing was the one measurement that settled it, which was simply watching long enough to see the thing fade. It is worth sitting with what that sequence actually was, because it is easy to file it under scientists being wrong, and that is not what happened. Callas's data were real. The object was there. It moved. It was photographed repeatedly across years by the best instrument available, and the analysis was careful. The interpretation was the most reasonable one available, given a sharp-edged debris ring and a moving point of light inside it. For 12 years, that image hung in textbooks and in museum halls, captioned as humanity's first photograph of another world. And the thing in the picture had already stopped existing before most people saw it. Two objects, the size of small moons, had struck each other, thrown up a cloud of fine dust, bright enough to outshine an actual planet in reflected light, and that cloud was already dispersing while the press release was being written. We had not photographed a world. We had photographed the aftermath of something being destroyed and mistaken it for something being born. Gaspar's own comment on it was that they had been in the right place at the right time to have witnessed such an unlikely event. Which is the honest reading? The odds against catching a 200-kilometer collision in a specific nearby system during the specific decade when a telescope capable of imaging it existed are enormous. We did not miss a planet. We got very lucky and saw something rarer. JUICE returned to the system in 2023. Gaspar Wolf and colleagues published mid-infrared imaging in Nature Astronomy that May, showing 3 nested belts extending out to roughly 23 billion kilometers from the star, an inner disk, then a gap near 78 astronomical units, then an intermediate belt near 90 that appears misaligned with the outer one, then another gap, then the outer ring. The 2 inner belts had never been imaged before. The gaps imply shepherds we still have not seen. JUICE's near-infrared camera also looked for the object directly and did not find it, which is exactly what the dust cloud interpretation predicts and exactly what a real planet would have contradicted. The same program did turn up 10 separate sources within the Fomalhaut rings, one of which, designated S7, remains a candidate planet awaiting follow-up. So the search that began in 2005 is not over. It has simply moved on to better candidates. There was one more twist. A compact clump in the outer ring was named the Great Dust Cloud and interpreted as possibly a second collision. Within days, archival data from ALMA and from Keck showed emission at that same position on the sky 6 to 18 years earlier, with no shared motion. It is a background object. Gaspar's response was that it was really unlucky, though not at all improbable, and that this is how science works. The name Dagon, chosen by public vote in 2015, still formally attaches to an object the catalogues no longer list. The next place holds a planet that has been there since the universe was young. Number 12, the Methuselah planet. Just outside the core of the globular cluster Messier 4, in Scorpius, there is a planet that is older than almost everything. Messier 4 is the nearest globular cluster to the Sun, somewhere between about 5,600 and 7,200 light-years away, and roughly 75 light-years across. Globular clusters are among the oldest structures in any galaxy, dense spherical swarms of hundreds of thousands of stars, formed early and largely unchanged since. Messier 4 was the first one in which individual stars were ever resolved, by Charles Messier himself in 1764. The planet's age is usually quoted at about 12.7 billion years. The universe is about 13.8 billion years old. This planet formed roughly 1 billion years after the beginning, and it is nearly 3 times the age of Earth. That age was not measured on the planet. It is inherited, and the logic is worth following. Every star in a globular cluster forms at essentially the same time, out of the same collapsing cloud. Planets form alongside their stars, out of the same material, in the same few million years. So a planet in a globular cluster carries the cluster's age. Messier 4's age is put at 12.7 billion years in the planet literature, and at 12.2 in some other analyses, and the system age is elsewhere given as 12.7 to 13. Whichever figure you take, the conclusion is the same. This planet formed in the first billion years of cosmic time. The system it belongs to is a triple, and each member is unusual. The first is a millisecond pulsar, PSR B 1620-26A. It is a neutron star of 1.34 solar masses, about 20 kilometers across, spinning roughly 100 times every second. The second is a white dwarf of 0.34 solar masses, with a temperature no higher than 25,200 Kelvin. It is notably young and notably hot, and that detail is going to matter. Those two orbit each other at about 1 astronomical unit, once every 6 months. And around both of them, at 23 astronomical units, a little wider than Uranus's orbit, is a planet of roughly 2.5 Jupiter masses, with an orbital period of about 95 to 100 years. It was the first circumbinary planet ever confirmed, and it remains one of very few planets ever found in any globular cluster. It is worth pausing on what that planet's sky would look like, because the arrangement has no counterpart anywhere near us. From 23 astronomical units out, the two central objects are close enough together to appear almost as one, and neither is a normal star. One is a white dwarf, a stellar core the size of Earth, radiating leftover heat at 25,000 Kelvin, blue-white and tiny. The other is not visible at all in ordinary light. It is a neutron star, 20 kilometers across, sweeping a beam of radio emission around 100 times a second. Beyond them, filling a substantial portion of the sky, is the cluster itself, hundreds of thousands of ancient stars, packed close enough that from inside the core, the night would never be fully dark. Now for how it got there, which is the strangest part. A supernova is not a survivable event for a planetary system. The star that became this neutron star would have exploded, shedding most of its mass in the process, and a system losing that much mass that quickly does not hold onto its planets. They are simply released. So the planet almost certainly did not form around the neutron star. The favored history goes like this. The planet formed around an ordinary main sequence star, the object that is now the white dwarf. Meanwhile, the neutron star existed separately, probably with a companion of its own. In the crowded core of a globular cluster, close encounters between stars actually happen, which almost never occurs in the galactic disk where we live. In one such encounter, the neutron star captured the ordinary star and its planet together into a bound orbit, and in the exchange it probably ejected whatever companion it had before. Then the captured star aged. It swelled into a red giant, expanded past the point where its own gravity could hold its outer layers against its neighbor's pull, and began pouring material onto the neutron star. That phase lasted a few 100 million years, and the transferred material carried angular momentum with it. The neutron star spun up. That is why it is a millisecond pulsar today. Its rotation is the recorded fingerprint of the theft. The donor's core, stripped of its envelope, became the white dwarf we see. The discovery arrived in stages over a decade. In the early 1990s, a group led by Donald Backer, studying what they believed was an ordinary binary pulsar, found that the timing residuals required a third body. Pulsar timing is astonishingly precise. A millisecond pulsar's rotation is stable enough that a distant companion betrays itself through shifts of microseconds in the arrival time of its pulses. In 1993, Stephen Thorset and collaborators showed the third object was too light to be a star. Then, on the 10th of July, 2003, Stein Sigurdsson, with Harvey Richer, Brad Hansen, Ingrid Stairs and Thorset, announced that Hubble had detected the white dwarf and that it had exactly the properties the exchange encounter model predicted, including its youth and its temperature. The paper's subtitle was Evidence for Early Planet Formation. The nickname Methuselah was introduced at the NASA briefing that day. The reason the discovery mattered was chemical, not architectural. Messier 4's iron abundance is about 8.5% of the Sun's. Planet formation is supposed to depend on heavy elements, because heavy elements are what solid planetary cores are built from, and in the early universe there were hardly any. A Jupiter mass planet forming in an environment that poor, that early, implies that planet formation began far sooner and under far worse conditions than anyone had assumed. The scarcity of such discoveries is part of the story. There are about 150 globular clusters known in the Milky Way, and they have been searched repeatedly with several different techniques, for decades. Despite that, planets in globular clusters remain among the rarest detections in the field. Whether that is because the metal-poor environments genuinely struggle to build planets, or because dense stellar traffic strips them away over billions of years, or simply because they are very hard to detect at those distances, is not settled. That has a consequence, and it is the reason this entry sits where it does on the list. If planets could form that early, then planets have been available for most of the universe's existence. Every process that requires a planet to happen on, and every span of time that requires a stable surface, has had roughly 8 billion years more to run than it has had here. Whatever has happened on Earth, in whatever order, could have happened elsewhere and finished before our star existed. There is an ending to this system, and it is already scheduled. The triple is heavier than an average cluster member, and in a globular cluster, heavier objects sink toward the center. It is on its way in. Within about 1 billion years, another close encounter is likely, and the standard outcome of a close encounter is the ejection of the lightest member. The planet will be thrown clear of Messier 4 entirely, to drift through the halo of the galaxy with no star at all, a body older than almost anything, alone, in the dark, permanently. The next place is the closest example of what our own sun will build when it dies, and nobody can explain its shape. Number 11, the red rectangle. About 2,300 light-years away, in Monoceros, there is an object shaped like nothing else in the sky. It is catalogued as HD 44179. Everyone calls it the red rectangle. It was found in 1973, during a rocket flight carrying an infrared survey run by the Air Force Cambridge Research Laboratories. It turned up simply as an unusually bright infrared source, one entry among many. The central star had actually been catalogued as a double by Robert Grant Aitken as far back as 1915, but nobody had reason to look closer. Martin Cohen, C. Monsieur. Anderson, George Coyne and colleagues named it and characterized it in a 1975 paper, establishing it as a carbon-rich object in the brief phase after a star like the Sun has finished burning, and before its exposed core is hot enough to light up the gas it has thrown off. That phase is called a pre-planetary nebula, and it does not last. Perhaps 1,000 years, out of a stellar lifetime of 10 billion. The red rectangle is the nearest example we have, which means it is the nearest available preview of what the Sun is going to build. The scale is smaller than the drama suggests. The nebula's radius is about 0.14 light-years, which is roughly 1/10 of the distance from the Sun to the nearest star. At 2,300 light-years, that is comfortably resolvable by Hubble, and that combination, close enough to resolve and small enough to see whole, is why this object has been studied so intensively for 50 years despite being faint. The center is a binary. There is a post-giant phase primary of about 0.8 solar masses, with a surface temperature near 8,000 Kelvin, and a companion of roughly solar mass carrying an accretion disk and a jet. They orbit each other every 318 days, plus or minus 3, on a moderately eccentric path. We have never seen either of them. The binary is completely obscured by a dense torus of dust sitting around it, edge-on from our viewpoint. Every photon we have ever received from this object has bounced off the surrounding nebula first. We know the orbital period from spectroscopy of scattered light. The stars themselves are behind a wall. The nebula is not actually rectangular. It is a bipolar outflow, two cones pointing in opposite directions from the center, and its edges happen to be so straight and so sharp that when you view it almost exactly side-on, the outline reads as a rectangle with an X through it. What makes it famous, though, is not the outline. It is what crosses it. The edges of the cones are bridged by a series of linear features running perpendicular to the outflow. Rungs. Evenly spaced, one above another, like a ladder laid across the whole structure, or a web spun between the two edges. Hubble imaged them properly with its Wide Field and Planetary Camera 2 in March of 1999, and the release that followed in 2004 was titled, reasonably enough, A Stairway to Heaven. The leading explanation for the rungs is that their spacing is close to periodic, which points at discrete episodes of enhanced mass loss from the central star, separated by a few hundred years. On that reading, each rung is a shell, a ring of material thrown off in one event, and we are seeing a stack of them edge on, so that each ring appears as a line. The total time over which the visible nebula was shed works out at around 14,000 years. That explanation is plausible, and it is not settled. The shaping of the whole structure remains contested between shock interactions among successive phases of the stellar wind and a jet from the companion sweeping around as it precesses. The X-shape is peculiar even for this class of object, and the outflow velocity is unusually low. The red rectangle was the first nebula around an evolved star in which a stable rotating equatorial disk was clearly identified, which is probably why its outflow behaves so differently from the purely expanding envelope seen elsewhere. Material is not simply being blown off. It is being drawn from something that is spinning. ALMA followed up in 2013 and confirmed the rotating disk that Boujarabal and colleagues had first identified in 2005. That confirmation matters more than it sounds. Almost every evolved star we observe shows an envelope that is simply expanding outward. A stable, rotating, long-lived disk around a dying star is rare, and it changes what the object can do. A rotating reservoir can be tapped slowly and repeatedly, which is a plausible route to a structure with rungs in it, rather than a smooth shell. And then there is the color, which is where the object stops being merely odd and becomes genuinely unsolved. The red in red rectangle comes from what is called extended red emission, a broad emission band centered near 6,400 angstroms, produced when something in the nebula absorbs ultraviolet light from the center and re-emits it in the red. The carrier of that emission has never been identified. Candidates include large aromatic hydrocarbon molecules, hydrogenated amorphous carbon, and silicon nanoparticles. Nobody has been able to choose between them. The object also shows the unidentified infrared bands, a set of emission features seen across the galaxy and generally attributed to aromatic hydrocarbons. The general attribution is widely accepted. The specific molecules producing them have never been pinned down. Then, in 1995, Peter Sare, Keith Miles, and Stanley Scarrett published something in Science that connected the red rectangle to one of the longest-running unsolved problems in astronomy. Diffuse interstellar bands were first noticed in 1919. They are absorption features that appear in the spectrum of essentially any star whose light has crossed a significant amount of interstellar space. Several hundred of them are now catalogued. They are produced by something out there in the gas between the stars, absorbing at very specific wavelengths, and for over a century nobody has been able to say with confidence what most of them are. It is one of the oldest open questions in the field. What Sare and his colleagues showed is that the red rectangle's own emission bands, near 5,799, 5,853, and 6,616 angstroms, shift in wavelength and narrow in width as you move outward from the central star. And in the limit of large distance from the center, they converge on the wavelengths of known diffuse interstellar bands. The reading is that the same molecular carriers are doing both jobs. The unidentified thing absorbing across the galaxy is the same unidentified thing emitting here, and here we can watch it change as conditions change. Which makes this single object the best laboratory in existence for a problem that has been open since 1919, and it is only 2,300 light-years away. There is one more contradiction, and it may be the strangest thing about the object. In 1998, Waters, Kami, de Jong, and colleagues reported in Nature that the equatorial disk contains oxygen-rich crystalline silicate dust, while the bipolar outflow above and below it is carbon-rich and full of aromatic hydrocarbons. One object, two incompatible chemistries, sitting one inside the other. The favored reading is that the star's oxygen-to-carbon ratio flipped during its late evolution, so the disk is storing the older material while the outflow reflects the newer phase. A competing reading is that the hydrocarbons are being manufactured in place by ultraviolet chemistry near the center, in which case no chemical flip is required at all. And the ultraviolet itself is a problem. A star at 8,000 Kelvin does not produce nearly enough ultraviolet light to excite what we see. Something else is supplying it, most likely a hot companion or the accretion disk around it, but that has not been demonstrated. The next entry is a cloud with 10 million solar masses of gas and a chemistry set nobody designed. Number 10. Sagittarius B2. We are halfway down the list, so it is worth taking stock of the distance covered. We began on a crater floor on Mercury, moved to a shadow on our own moon, then to the bottom of a basin on Mars. From there we went out to the nearest brown dwarfs, 6 light-years away, and onto a handful of worlds a few hundred light-years off. The last entry was a dying star 2,300 light-years away. Everything so far has been, in galactic terms, local. That ends now. The next place is 26,700 light-years away, at the center of our own galaxy. Sagittarius B2 is a giant molecular cloud sitting roughly 350 light-years, in projection, from the black hole at the galactic core. It contains something like 10 million solar masses of gas, inside an envelope about 145 light-years across. That makes it one of the most massive molecular clouds in the Milky Way. Its mean density is around 3,000 hydrogen particles per cubic centimeter, which is 20 to 40 times denser than a typical molecular cloud, and its inner regions reach 100,000. Its bulk temperature runs between about 20 and 40 Kelvin. It is, in other words, cold, dark, extremely large, and by the standards of interstellar space, crowded. By the standards of anything else, it is not crowded at all. 3,000 particles per cubic centimeter sounds like a lot until you compare it to the air in the room you are sitting in, which holds about 25 billion molecules in that same volume. Sagittarius B2 is a better vacuum than any laboratory on Earth can produce. Hold that thought, because it matters shortly. Inside the cloud are two main sites where massive stars are forming, called Sagittarius B2 North and Sagittarius B2 Main, separated by about 6 light-years in projection, each around 50,000 solar masses. A third, South, is less active. And buried inside North is a hot core with a name that tells you its reputation, the large molecule Heimat. Heimat is German for home. It is where the large molecules live. Its density exceeds 10 million particles per cubic centimeter, and its gas temperature is around 100 Kelvin, which for interstellar chemistry is warm. That warmth is the point. Interstellar chemistry mostly happens on the surfaces of dust grains. Molecules build up slowly as ices in the cold, over enormous spans of time, and then a young star nearby heats the grains and everything evaporates off at once into the gas, where we can see it. The large molecule Heimat is a place where that has recently happened, on a large scale, in a cloud that had a great deal of time to prepare. The large molecule Heimat itself is small. On the sky, it spans about 2 arcseconds, which at that distance corresponds to a region roughly a quarter of a light-year across. So the single most chemically productive location known to astronomy occupies a volume smaller than the gap between the Sun and its nearest neighbor, buried inside a cloud 145 light-years wide, 26,000 light-years away, behind essentially the entire thickness of the galactic disk. The result is that roughly a third of all the molecular species ever identified in interstellar space were first found here. The current catalogue of known interstellar molecules runs past 300. One cloud, out of the entire galaxy, supplied about 100 of them. In 2009, Arnaud Belloche and colleagues, using the 30-meter telescope at Pico Valletta in Spain, reported 2 more. The first was ethyl formate, an 11-atom ester. The second was N-propyl cyanide, a 12-atom molecule, which at the time was the largest single interstellar molecule found outside the long carbon chains. The way the survey was conducted deserves a mention too, because it was not a targeted search. Belloche and colleagues ran a blind line survey. They scanned across the whole 3-millimeter band, recorded every emission feature they found, and then set about identifying them afterward. That is a slow and unglamorous way to work, and it is the reason the result was 2 new molecules rather than 1 confirmation. They were not looking for ethyl formate. They were looking at everything, and ethyl formate was in the data. The scientifically important one was the second, and specifically its shape. N-propyl cyanide has a branched carbon skeleton. The chain of carbon atoms does not run straight, it forks. Amino acids are branched. Finding branched chemistry happening on its own in interstellar space, without anyone arranging it, was the actual result of that paper. What the world heard was that the center of the galaxy tastes of raspberries and smells of rum. It is worth being precise about how that happened, because the anatomy of the distortion is instructive. Ethyl formate does contribute to raspberry flavor, and it does carry a faint rum-like odor. That much is true. It is not the raspberry compound. The dominant one is raspberry ketone, which has never been detected in Sagittarius B2 or anywhere else in space, and full raspberry flavor additionally requires ionones and several other compounds, none of which have been found either. Belloche said this directly, at the time, to The Guardian. Ethyl formate happens to give raspberries their flavor, he told them, but many other molecules are needed to make space raspberries. The qualification did not survive retelling. 3 other things also failed to survive. It was one cloud, not space in general. Ethyl formate was one of roughly 50 molecules that survey detected, sitting alongside hydrogen cyanide and the N-propyl cyanide itself, which is toxic. And at 3,000 particles per cubic centimeter, there is nothing there to taste or smell in any case. You could not detect it. There is not enough of anything, anywhere in that cloud, to register on a human sense. The list of things first found in Sagittarius B2 is genuinely long. Vinyl alcohol, by Turner and Aponi in 2001. Glycolaldehyde, by Hollis and colleagues in 2000. Ethanol, by Zuckerman and colleagues in 1975. Aminoacetonitrile, by Belloche in 2008. Isopropanol in 2022. Ethanamine, a possible precursor to the amino acid alanine, found by Loomis and colleagues in 2013 using the Green Bank telescope, though in foreground gas rather than in the hot cores themselves. Dust temperature in the cloud runs warmer than usual as well, around 50 to 70 Kelvin, noticeably higher than comparable star-forming regions out in the galactic disk. That is another consequence of the neighborhood. The whole central region of the galaxy is bathed in more radiation and more turbulence than anywhere we live, and Sagittarius B2 sits in the middle of it, being cooked gently from all directions. There is one conspicuous absence. Glycine, the simplest amino acid, has been searched for in this cloud repeatedly by multiple groups over decades. It has never been convincingly detected. Now for the second reason Sagittarius B2 is on this list, which has nothing to do with chemistry. The cloud glows in X-rays, specifically in the iron line at 6.4 kilo-electron-volts, which is what iron produces when it is illuminated by hard radiation from outside. Sagittarius B2 is not generating that light. It is reflecting it. The cloud is acting as a mirror. What it is reflecting is an outburst from the black hole at the center of the galaxy. Because the cloud sits well behind the black hole from our viewpoint, the light took a longer path to reach us than the direct light did, and the delay works out at roughly 300 to 400 years. Analyses across Chandra, XMM Newton, ASCA, and integral data converge on the same conclusion. About 300 years ago, the galactic center was around 1 million times brighter than it is now. That reflected glow has been observed fading through the 2000s as the illuminated region moves on. So what we are looking at is a cloud displaying, in real time, an event that finished before the telescopes existed. The outburst is over. It ended centuries ago. We are watching the last of the light from it cross a cloud that happened to be standing in the right place. The next place has been drawing a corkscrew across 300 light-years for tens of thousands of years. Number 9, SES 433 and the Manatee Nebula. In 1977, Bruce Stevenson and Nicholas Sanduleek at Case Western Reserve University published a catalogue of stars with unusual emission lines. The 433rd entry was an object about 18,000 light-years away in Aquila. It has been known as SS 433 ever since. In 1978, Clark and Murdin took the first proper optical spectrum of it, and the result made no sense. Spectroscopy is the most reliable identification tool in astronomy. Every element produces emission at specific, known wavelengths, and you read them off. The lines from SS 433 did not match anything. They were not the lines of any element because they were not at the wavelengths any element produces. Bruce Margon and his collaborators solved it in 1979, and the solution reframed what the object was. The strange lines came in pairs. For each one there was a partner. One strongly shifted toward the red end of the spectrum, and one strongly shifted toward the blue. And the pairs moved. Over months, they swept back and forth through the spectrum in a cycle lasting about 164 days. The only interpretation that worked was that the object was firing two opposed jets of material at a substantial fraction of the speed of light, one roughly toward us and one roughly away, and that the whole jet axis was swinging around like a sprinkler. The lines were ordinary hydrogen. They were simply Doppler shifted so violently and so variably that they had stopped looking like hydrogen. The measured jet speed is 0.26 times the speed of light, 78,000 kilometers per second. At that speed, you would cross from the Earth to the Moon in under 5 seconds. And it has stayed at that speed, essentially unchanged, for over 4 decades of measurement, which is itself remarkable, because almost nothing in accretion physics is that steady. The geometry is precise. The precession period is 162.375 days, about an axis inclined some 78 degrees to our line of sight, with the jets sweeping out a cone of 20 degrees half angle. The binary at the center orbits every 13.082 days. Radio interferometry has resolved the jets down to subastronomical unit scales, and what it shows is exactly what the geometry predicts. a corkscrew, a helix of material laid down in space as the launch point swings around. Because the precession sweeps that cone every 162 days, the Doppler shift of the jet lines swings through its full range roughly 5.5 months at a time, and then reverses. Margon's team were watching hydrogen lines migrate across thousands of angstroms of spectrum and come back. That is why the object was so hard to identify and so satisfying to solve. The answer explained not just where the lines were, but why they refused to stay there. Ride out along one of them. The material leaves the system at 78,000 kilometers per second, and it does not slow down. It is not being pushed continuously. It was accelerated at the base and then released, and now it simply travels. Behind you, the launch point is not holding still. Over the course of 162 days, it sweeps through a 20-degree cone and returns, which means the material released tomorrow leaves in a slightly different direction than the material released today. So what is written into space behind you is a spiral. Not a line, a spiral, each turn of it 162 days of the system's history laid out in the order it happened, unwinding outward. From alongside, you cannot see the shape. You are inside one strand of it, moving straight, and every other strand is somewhere off in the dark, traveling parallel and slightly aside. Then, several hundred light-years ahead, there is a wall. The remnant of an old supernova, expanding gas that has been there far longer than this jet has existed. And it is not shaped the way such a remnant should be, because material, like the material you are riding in, has been arriving at that spot, at a quarter of the speed of light, for tens of thousands of years, and it has pushed the wall outward into a shape it would never have taken on its own. That remnant is called W50, and its popular name is the Manatee Nebula. It spans about 2 degrees by 1 on the sky, which at 18,000 light-years means something like 650 light-years by 350. It is one of the largest supernova remnants in the galaxy. A supernova remnant should be roughly spherical. An explosion goes off, the shell expands outward evenly in every direction, and unless it runs into something lopsided, it stays round. W50 is not round. It has a central shell about a degree across, and then 2 elongated ears extending northwest and southeast, exactly along the axis the jets precess about. The jets have punched through the shell and inflated it in both directions. The scale relationship there is worth stating carefully. The binary system at the center is, generously, a few tens of kilometers across at its business end. The structure it has reshaped is hundreds of light-years wide. An object smaller than a city has bent something larger than most of the constellations you can name. The observational record on the jets has thickened considerably in recent years. NuSTAR detected hard X-rays from the eastern jet in 2022 and from the western one in 2025. Near-ultraviolet work in 2024 provided evidence that one of the jets is interacting directly with a molecular cloud designated N4, which is to say, the jet is not merely crossing empty space, but running into things and lighting them up. In 2026, Irosita produced a full X-ray panorama of the whole remnant. And a 2025 result measured for the first time the proper motion of the acceleration regions themselves, which are moving. What that binary actually is has not been settled in over 40 years, which is unusual for an object this well studied. The companion is clear enough, an A-type supergiant of roughly 10 solar masses, swollen past the boundary where its own gravity can hold its outer layers, pouring material across onto its partner. The partner is the argument. Estimates have ranged from 1 to 30 solar masses. Dodorico and colleagues argued in Nature in 1991 that it is a neutron star. Goransky's photometric analysis in 2011 also favored a neutron star. On the other side, mass ratio work by Cherepashchuk and colleagues in 2018 and 2019 gives a total system mass around 15 solar masses, with the compact object near 8, which would make it a black hole, and X-ray spectral arguments point the same way. The current balance of opinion leans toward a black hole of 5 to 10 solar masses. It is worth attributing that rather than asserting it, because the case is genuinely open. What the system does is clearer than what it is. SS433 is the archetype of supercritical accretion. Material is falling onto the compact object far faster than the theoretical limit at which radiation pressure should blow the infalling gas back out. The disk responds by going thick, driving a radiation-supported outflow and forming a funnel. The system radiates around 10 to the 40th ergs per second, and much of that is reprocessed and beamed away from us by the funnel walls, which means we have never seen the innermost region directly. Everything we observe is second-hand light. One further detail argues that something structural is going on, rather than something incidental. The system's orbital period has been observed to be increasing, a result published in 2025. An orbital period that changes measurably over decades is a strong constraint on how much mass is being transferred and where it is going, and it is one of the few handles anyone has on the mass transfer history of a system whose inner regions are permanently hidden from view. It is also the prototype microquasar, a term coined by Félix Mirabel and Luis Rodriguez in 1994, for a stellar mass compact object producing collimated relativistic jets. The idea is a scaling argument. A quasar is a supermassive black hole with an accretion disk and jets operating over millions of years. A microquasar is the same architecture with the mass reduced by a factor of 100 million and every timescale compressed to match. Processes that take a quasar a million years take SS433 a few days. It is a quasar we can watch on a human schedule. The most recent chapter concerns what happens where those jets stop. In 2018, the Hawke Observatory reported in Nature that the very high-energy gamma rays from this system do not come from the binary at all. They come from the jet lobes, hundreds of light-years out, coincident with the X-ray knots, where the jets are plowing into the remnant. HESS. Followed in 2024 with energy-dependent structure across 1 to 30 tera-electron volts, finding that higher energy photons sit closer to the inner lobes, which is direct evidence of a particle acceleration site located partway along a jet rather than at its base. Lasso sees the lobes as two point-like sources from 1 to 25 and 25 to 100 tera-electron volts, with emission migrating toward the center above 100. For scale, the Large Hadron Collider accelerates protons to about 7 tera-electron volts. These lobes are producing photons above 100, which means the particles making them are at energies well beyond anything we have built. SS433 is a candidate, Pevatron, a natural accelerator operating in our own galaxy, at energies no machine on Earth approaches, and it has been running continuously for as long as there have been people to not notice it. The next place packs a substantial fraction of the galaxy's most massive stars into 6.5 light-years. Number 8. Westerlund. 1. Bengt Westerlund found it in 1961 and gave it a title that undersold it considerably, a heavily reddened cluster in Ara. Then it sat, largely unstudied, for decades, because the dust between us and it is thick enough to make the work genuinely difficult. Westerlund 1 is now regarded as the most massive young star cluster in the Milky Way. Its distance was revised upward once Gaia's parallax measurements arrived. The older figure was about 3.8 kiloparsecs. Navarrete and colleagues got 4.06 in 2022. Negarela and colleagues got 4.23. Rocha and colleagues got 4.03, using an eclipsing binary within the cluster as a distance standard. The weighted mean lands near 4.05 kiloparsecs, about 13,000 light-years. Why the cluster went unexamined for so long is worth explaining, because it is a recurring problem in this part of the sky. Westerlund 1 sits in the plane of the galaxy, and the line of sight to it passes through a great deal of interstellar dust. Dust scatters blue light more effectively than red, so anything seen through it arrives dimmed and reddened, and the correction required is large and uncertain. Working out how much light has been removed, and therefore how bright the object actually is, and therefore how far away it is, becomes a chain of estimates. Gaia's direct parallax measurements were what finally broke that chain. Its total mass is usually given as somewhere between 50 and 100,000 solar masses, with 63,000 a commonly cited figure. And the core region is about 6.5 light-years across. Hold those two numbers next to each other because their ratio is the entry. In the neighborhood of the Sun, the average separation between stars is roughly 5 light-years. Our nearest neighbor, Proxima Centauri, is 4.24 light-years away, and between here and there is nothing at all. Westerlund 1 fits hundreds of supergiants inside a sphere that, out here, would comfortably hold one star and its empty surroundings. The census is the part that stops people. 6 yellow hypergiants, 4 red supergiants, 24 Wolf-Rayet stars, which are massive stars in the final phase before they explode, having already blown away their outer layers to expose the fusing core beneath. The entire Milky Way is thought to contain a few hundred Wolf-Rayet stars in total. 24 of them are inside this one 6 light-year sphere. There is also a luminous blue variable, catalogued W243, and a peculiar object designated W9, which has been proposed as the remnant of 2 stars that merged and is the brightest radio source in the cluster. The largest member is Westerlund 1-26, a red supergiant with a current radius estimate between 1,165 and 1,221 times the Sun's. Older estimates ran as high as 2,500 solar radii and are now considered unlikely. Even at the lower figure, if you placed it where the Sun is, its surface would extend past the orbit of Jupiter. It has a luminosity of 320 to 380,000 suns, and it is surrounded by its own ionized nebula. 3 other red supergiants in the cluster, catalogued W237, W20, and W75, run from 668 to 1,245 solar radii. The binary statistics add another dimension to the crowding. Surveys with the Very Large Telescope established that about 70% of the Wolf-Rayet stars in the cluster have companions, and more than 40% of the massive blue supergiants do. In a cluster this dense, binaries are not incidental. They are the mechanism by which stars strip each other, exchange mass, and end up on evolutionary paths that a solitary star of the same mass would never take. Some of the strangest objects in the cluster are probably the products of that, rather than of ordinary single-star evolution. The cluster's age is currently an argument, and it is a live one. The classical figure was 4 to 5 million years, derived from the fact that Wolf-Rayet stars, red supergiants and yellow hypergiants all coexist there. Red supergiants take about 4 million years to appear. The Wolf-Rayet population collapses after about 5. The overlap is narrow, so the age looked well constrained. Then the distance moved. A cluster further away is intrinsically brighter than previously thought, which changes the mass of the most massive stars still on the main sequence, which changes the age. The revised numbers drop the main sequence turnoff from 40 solar masses to 22, implying an older cluster. Rocha and colleagues proposed roughly 7 million years for the massive blue stars, but 10.7 million for the red supergiants, which would mean the cluster did not form all at once. That is a real tension with the classical picture, and it has not been resolved. Then there is the magnetar. XIOJ 164710.2-455216 is the most luminous X-ray point source in the cluster. It was found by Muno and colleagues in 2006 in a paper titled Plainly, a neutron star with a massive progenitor. A magnetar is a neutron star with an extraordinarily strong magnetic field, around a quadrillion times Earth's. At a distance of 1,000 kilometers, a field like that would erase the magnetic strip on a credit card. Considerably closer in, it disrupts the structure of atoms themselves. The reason this one caused a problem is the same reason globular cluster ages work. Everything in the cluster formed at the same time. So whichever star produced this magnetar must have been more massive than the stars still surviving on the main sequence today, because it has already finished its life while they are still working through theirs. That implied a progenitor above 40 solar masses. Clark and colleagues used an eclipsing binary in the cluster to tighten it in 2010, ruling out a progenitor below about 35 solar masses and supporting something above 45. Standard stellar evolution says a star that massive collapses into a black hole. It does not leave a neutron star behind. Either very massive stars can shed enough material through winds or through interaction with a binary companion to end up under the threshold anyway, or the thresholds themselves are wrong. It is worth adding that the Gaia distance revision, by lowering the turn-off mass, weakens the original inference. So this is unsettled rather than solved. There is a second absence in the cluster, and it may be the more troubling one. Models predict that between 50 and 150 supernovae should already have detonated in Westerlund 1, roughly one every 10,000 years across the past million. That is not a subtle prediction. 50 to 150 stellar corpses should be sitting there. One is definitively detected. The candidate explanations are that supernovae impart violent kicks at birth, flinging the resulting neutron stars and black holes clear of the cluster entirely, that the remnants are quiescent stellar mass black holes with nothing falling onto them, which emit essentially nothing and are close to undetectable, or that they are hidden in tight pairs with each other. Probably some combination. But the plain observational statement is that the most crowded young cluster we know of appears to have mislaid over 100 dead stars. Just observed the cluster in a program published in early 2025, revealing diffuse nebulosity around the core, made of droplet-shaped features that all point toward the groups of massive stars, sculpted by their combined winds. Its mid-infrared instrument resolved shells and outflows around several of the red supergiants at a level of detail nobody had achieved before. A Hubble study in 2025 measured the cluster's crossing time at about 300,000 years and found clear mass segregation, with the heaviest stars concentrated toward the center. And there is a projection worth ending on. Westerlund 1 is expected to survive long enough and stay bound tightly enough to evolve into a globular cluster. Globular clusters are 12 billion years old. This one is a few million. We are looking at the youngest example of a class of object we normally only ever see as ancient, and everything currently inside it is going to explode. The next entry is a galaxy you could not see even if you were inside it. Number 7. Segue 1. In 2007, Vasily Belokurov and colleagues found a faint overdensity of stars in imaging from the Sloan Digital Sky Survey. It lies in Leo, about 75,000 light-years away, and it was catalogued as Segue 1. Belokurov's initial reading was that it was an extended globular cluster, possibly a piece stripped off the Sagittarius stream. That reading did not survive. The name itself is a small piece of survey history. Segue stands for the Sloan Extension for Galactic Understanding and Exploration, a sub-survey designed to map the structure of the Milky Way and its surroundings by measuring enormous numbers of faint stars. Objects like this one do not announce themselves. They are found by counting stars across the sky, noticing that a particular patch has slightly more than it should, and then going back to check whether those stars are moving together. Start with how much light it produces. The total luminosity of Segue 1 is about 300 times the Sun's. That is not 300 times the luminosity of a galaxy. That is the entire object. 300 suns worth of light in total from the whole thing. A single bright red giant star produces more. Segue 1 is the least luminous galaxy known, and it is fainter than individual stars you can see with the naked eye from a dark field on Earth. Only about 71 stars have ever been spectroscopically confirmed as members. The total population is of order 1,000 or fewer. Its half-light radius, the distance within which half its light is contained, is around 29 parsecs, or about 95 light-years. So the picture is a loose scattering of perhaps 1,000 ancient stars, spread across a region 100 light-years wide, producing collectively less light than one large star. And those stars are moving at 3.7 kilometers per second. That is the number that made Segue 1 important, and it takes a moment to see why. In any gravitationally bound system, the speed at which the members move tells you how much mass is holding them. Orbit slowly, and there is not much there. Orbit fast, and something heavy is doing the pulling. 1,000 faint stars, scattered across 100 light-years, should be barely bound at all. Their mutual gravity is negligible. They should be drifting apart, and their velocities relative to each other should be a fraction of a kilometer per second. They are not. They are moving nearly 10 times faster than the visible material could possibly explain. Run the arithmetic, and the mass within the half-light radius comes out around 580,000 solar masses. Divide by 300 solar luminosities, and you get a mass-to-light ratio of about 3,400. For an ordinary population of stars, that ratio runs between 1 and 5. Segue 1 has the highest dark matter density ever measured in any known object. Josh Simon and colleagues gave their 2011 paper the plain title, The Darkest Galaxy. But there was a serious objection, and it had to be dealt with before any of that could be trusted. A star cluster contains essentially no dark matter. A dwarf galaxy is dominated by it. If Segue 1 were a cluster being pulled apart by the Milky Way's tides, then some of the stars measured might not be bound to it at all, merely passing through on their way out. Unbound stars would inflate the apparent velocity spread. So would undetected binary stars, whose orbital motion would masquerade as motion within the system. Either could manufacture a fake dark matter halo out of nothing. Simon and colleagues set out to close both loopholes. Using the DEIMOS spectrograph on the Keck telescope, they obtained velocities for 98% of the stars within 67 parsecs of the center, down to the practical limit of the instrument. They observed at multiple epochs, so that any star whose velocity changed between visits could be identified as a binary and removed. And they ran a full statistical membership analysis rather than assuming everything in the field belonged. The velocity dispersion held, but the evidence that actually settled it turned out to be chemical rather than kinematic, and it is elegant. A star cluster forms from a single cloud of gas that was thoroughly mixed before collapse. Every star in it, therefore, has essentially the same composition, and clusters show almost no internal spread in metal content. Segue 1 shows an enormous one. Its mean iron abundance is around 2.7 decs below solar, meaning about 1/500th of the Sun's iron, with a scatter of about 0.7 decs around that. At least 2 of its stars sit below 3 decs. One of them is an extremely carbon-rich, extremely metal-poor star at -3.5. The carbon-rich star deserves its own note. Stars that are both extremely poor in metals and unusually rich in carbon are thought to preserve the chemical output of the very first generation of massive stars, the ones that formed out of pristine hydrogen and helium and had no heavy elements at all to begin with. Finding one inside, Segue 1 is a strong statement about when this object stopped evolving, because that signature would have been overwritten by later generations, if there had been any. A spread that large cannot come from a single well-mixed cloud. It requires multiple generations, stars forming, exploding, enriching the gas around them, and the next generation forming out of that enriched gas. And crucially, it requires that the system was able to hold on to its own supernova ejector rather than losing it to space. A supernova throws material outward at thousands of kilometers per second. 1,000 faint stars have nowhere near enough gravity to retain that. Something with a great deal more mass must have been holding the system together while it enriched itself. That is a galaxy, not a cluster. The chemistry proves the halo. Anna Friebel, Simon and Evan Kirby went further in 2014, titling their paper An Unevolved Fossil Galaxy from the Early Universe. Segue 1 stars carry the chemical fingerprint of enrichment by only a handful of the very first supernovae, and essentially nothing after that. No contribution from the slower processes that dominate later chemical evolution. Which means star formation there began, ran briefly, and stopped, and never restarted. Segue 1 has been chemically frozen for roughly 13 billion years. It is a surviving piece of the era before the first galaxies had finished assembling, still bound, still orbiting, still there. It is worth noting that not everyone accepts the standard interpretation. A study published in 2025 modeled the system with a central supermassive black hole supplying the extra gravity instead of a dark matter halo. That is an emerging minority position rather than a consensus, and it is worth attributing rather than dismissing, because the observable it is trying to explain is the same one. Something invisible in that galaxy is doing a great deal of gravitational work. Its properties also make it one of the best targets anywhere for a particular kind of experiment. If dark matter is made of particles that annihilate when they meet, the annihilation should produce gamma rays, and the signal should be strongest where the density is highest. Galaxies will continue to drift. The stars overhead may appear eternal, but the great web of galaxies is always in motion. So it has been watched heavily. Magic observed it between 2011 and 2013 for around 160 hours, the deepest, very high-energy observation of any dwarf galaxy ever performed. Veritas spent 230 hours across 5 dwarfs, including this one. Fermi watched from orbit for 6 years. A joint analysis in 2016 combined the ground-based and space-based data across a range from 10 giga-electron-volts to 100 tera-electron-volts, the widest mass range ever explored in a single search of this kind. Nothing. No excess of any kind, at any energy. That null result has real consequence. It pushes the limits on how strongly dark matter particles can interact below the value that the simplest models require, which rules out large regions of the available parameter space. But the plain statement of it is the one worth keeping. The darkest object we know of, watched for hundreds of hours by the most sensitive instruments ever built, is also completely dark in gamma rays. The next place is 2 black holes, and we have been photographing it by accident since the 1880s. Number 6. OJ-287. OJ-287 is a blazar in Cancer, roughly 5 billion light-years away. A blazar is an active galactic nucleus whose jet happens to point almost directly at us, which is why small changes in the jet produce very large changes in apparent brightness. There are many blazars. What makes this one exceptional is the archive. OJ-287 lies near the ecliptic, the band of sky along which the planets and asteroids travel. For well over a century, astronomers have been photographing that band systematically, hunting minor planets. Every time they did, they caught this object too, incidentally, without knowing what it was, or caring. Its image appears on hundreds of photographic plates, going back to around 1890, principally in the Harvard plate stacks and the Sonneberg archive. The historical light curve was finally assembled in 1982, and outbursts from 1900 and 1913 were recovered and characterized afterward. Think about what that means. There is a continuous brightness record of this object stretching back before anyone knew that other galaxies existed. It was being photographed by accident during the decades when the nature of the spiral nebulae was still an open question, and the plates sat in cabinets, and the object kept doing what it does. The designation itself comes from the Ohio Sky Survey, which catalogued radio sources in the 1960s and gave them two-letter prefixes. OJ-287 was identified as a variable radio source there, decades before anyone connected it to the archive of accidental photographs already sitting in Massachusetts and Germany. The object had two separate observational histories, in two different parts of the spectrum, before anyone realized they belonged to the same thing. What it does is flare on a roughly 12-year cycle. And the flares are double-peaked, with two maxima separated by about a year. Sillanpää and colleagues proposed in 1988 that the cause was a binary black hole. Leto and Valtonen built the model still in use in 1996, and its mechanism is worth laying out because it explains the double peak exactly. A secondary black hole orbits a much larger primary, and the primary has an accretion disk around it. The secondary's orbit is inclined, so twice per orbit it passes through the plane of that disk, punching straight through it. Each impact heats a region of disk gas, which expands, becomes transparent, and releases a burst of thermal radiation. That burst is spectrally distinct from the ordinary flaring of the jet, and it is unpolarized, so it can be identified. 2 impacts per 12-year orbit produces 2 peaks, and because the orbit precesses, the timing shifts in a calculable way from cycle to cycle. The classical masses in this model are a primary of about 18 billion solar masses, and a secondary of about 150 million. Those numbers are now contested, and honesty requires saying so. A paper in 2023 argued the standard model requires substantial revision and that the primary is more plausibly around 100 million solar masses, which would be a factor of more than 100 smaller. The counter-argument from Valtonen's group is that general relativity is not scale-free, so a mass scale reduced that dramatically would destroy the model's 40-year record of correct predictions. Intermediate analyses land near 10 billion for the primary. And there is one clear failure on the record. The outburst predicted for October of 2022 did not arrive. There is a further piece of evidence that the binary is real, independent of the flare timing entirely. The orbit is decaying. A pair of black holes orbiting each other radiates gravitational waves, and radiating energy means the orbit slowly shrinks. That decay was confirmed in this system in 2008 and reconfirmed in 2023. It is a direct dynamical consequence of there being 2 objects rather than 1, and it does not depend on any model of what happens when a disk gets punctured. But the predictions are why this object matters, and 2 of them deserve telling properly. The first came in 2015. The model said a flare should peak in early December, and on the 5th of December 2015, OJ-287 reached its brightest optical level in 3 decades. It was named the Centenary Flare because it fell on the 100th anniversary of general relativity. From its precise timing, Valtonen and colleagues extracted the primary black hole's spin, 0.313, plus or minus 0.01. The second is better. The model predicted that the next disk impact would produce a flare peaking in the early hours of the 31st of July 2019, Universal Time, within a window of plus or minus 4.4 hours. It was named the Eddington Flare, after Arthur Eddington's 1919 eclipse expedition, the first observational test of general relativity, whose centenary it marked. Sit with the chain of reasoning that prediction rests on. It begins with glass photographic plates exposed in the 1890s by people looking for asteroids, developed and filed away. It runs through a 1982 effort to dig those plates out and measure them consistently enough to build a light curve across 90 years of changing instruments and emulsions. It runs through a model written in 1996, describing 2 black holes, one punching through the other's disk, in a system so distant that the light arriving now, left before the Earth, had complex life. And it produces an output that is not a general expectation, but a specific claim, that a particular brightening will peak on a named morning, within 4 hours. The Spitzer Space Telescope was pointed at it. This was one of the observatory's final campaigns. It was retired in January of 2020, months later. The flare arrived within 4 hours of the prediction. The reason that constitutes a physics result, rather than a good guess, is worth stating. The timing depends on how the secondary's orbit precesses, which depends on the shape of the primary's gravitational field, which depends on its quadrupole moment. For a rotating black hole in general relativity, that quadrupole moment is not a free parameter. It is fixed uniquely by the mass and the spin. So getting the timing right to within 4 hours out of 12 years is a test of whether a real astrophysical black hole has the specific field geometry that the theory says it must have. It is a parametric test of the no-hair theorem, and it is the only one ever performed on a binary black hole system. Modern instruments have added detail the plates never could. Tess watched the object continuously at 2-minute cadence for about 80 days in late 2021 and caught its flux nearly doubling and then nearly tripling within 2 days, with the fastest measurable variation occurring over about 9 hours. Radio interferometry using an orbiting antenna has resolved a ribbon-like structure in the jet. And a 2025 analysis examined magnetic reconnection triggered by the secondary's passage as a driver of the X-ray and radio behavior. The newest work concerns whether we can see the secondary at all, and the answer appears to be yes, indirectly. A large intraday optical flare on the 12th of November 2021 showed a change in spectral index, implying a new radiation component, most plausibly located in a jet belonging to the secondary black hole rather than the primary. In January of 2022, the Fermi telescope recorded the object's largest gamma-ray flare in 6 years, coinciding with an expected disk crossing. And a polarization campaign running from 2015 to 2023, across 7 telescopes on multiple continents, found something subtle. Normally, when this object brightens, its polarization rises too. There are moments when that rule breaks down, and those moments coincide with when the binary model says the secondary is active. 2 overlapping emission sources would produce exactly that. The 2 black holes are separated by about 10 microarc-seconds on the sky, which means no telescope that will ever be built can resolve them as 2 points. Polarization is the only tool that can tell them apart, and it appears to be working. The next place is where the universe demonstrated that most of what a thing is made of can pass straight through itself. Number 5. The Bullet Cluster. About 3.4 billion light-years away, two galaxy clusters ran into each other, and in doing so, they performed an experiment nobody could have designed. The object is catalogued as 1E0657-558. Everyone calls it the Bullet Cluster. It is a large cluster with a smaller one that has punched clean through it, roughly in the plane of the sky, which is the geometrical accident that makes the whole thing readable. Core passage happened about 150 million years ago as we see it. Used lensing work in 2025 and 2026 has finally pinned the mass ratio at about 10:1, settling 20 years of disagreement. To understand what the collision revealed, you need to know what a galaxy cluster is actually made of, and the answer is not what most people assume. It is not mostly galaxies. In a typical cluster, only about 2% of the mass is in stars. About 13% is in gas, an enormously hot, enormously thin plasma, filling the space between the galaxies at temperatures of tens of millions of Kelvin, radiating almost entirely in X-rays. So of the material we can actually see, the gas is the overwhelming majority. There is far more mass in the space between the galaxies than in all the galaxies combined. It is worth pausing on how strange that gas is as a substance. At 100 million Kelvin, it is far hotter than the core of the Sun. It is also about 100,000 times thinner than the air at sea level on Earth, thin enough that by any everyday standard, it is a vacuum. Temperature, at that density, is not something you would feel as heat. It describes how fast individual particles are moving, and there are so few of them that they would carry almost no energy to anything they struck. And yet, spread across millions of light-years, that near nothing adds up to more mass than every star in every galaxy in the cluster. The remaining 85% is the part nobody has ever detected directly. Now collide two of these. The gas is a fluid. When two clouds of gas meet at high speed, they cannot pass through each other. They shock, they compress, they heat, and they slow down. Chandra was granted more than 100 hours on this object, and the X-ray analysis led by Maxim Markovich shows exactly that. Bullet gas at about 70 million Kelvin ploughing into main cluster gas at about 100 million, producing a bow shock at Mach 3, one of the cleanest shock fronts ever seen in a cluster. The galaxies do something different. A galaxy is 100,000 light-years across, and the nearest other galaxy in a cluster is typically millions of light-years away. In collision terms, galaxies are point particles separated by enormous empty gaps. Two clusters of galaxies pass through each other, essentially without interacting at all. The galaxies sail straight on. So the collision separates the components. The gas piles up in the middle, shocked and glowing. The galaxies continue, out ahead. And that separation is what turns the object into an experiment, because it lets you ask a question that is otherwise impossible. Where is the mass? Douglas Clow and colleagues answered it using weak gravitational lensing. Mass bends light, so the images of distant background galaxies seen through a cluster are slightly distorted, stretched very subtly around the mass. No individual galaxy tells you anything. The distortion is far too small. But measure the shapes of many thousands of them, and the statistical pattern maps out where the mass is. Combining data from Hubble, the Very Large Telescope, and Magellan, they produced that map. The mass was not with the gas. The mass centroids sit out ahead with the galaxies. The great majority of the material in this collision passed straight through it without slowing, without compressing, without heating, without noticing that anything had happened. Their 26 paper carried an unusually direct title, a direct empirical proof of the existence of dark matter. The logic is worth following, because it is cleaner than most arguments in this area. If there is no dark matter, and instead our theory of gravity is simply wrong at these scales, then gravity must still be produced by the matter we can see. The overwhelming majority of the visible matter here is the gas. So the lensing signal should be centered on the gas. It is not. It is somewhere else, tracking something that behaves as though it barely interacts with anything, including itself. NASA's release of the 21st of August, 2006 was titled, "Without Hedging, NASA Finds Direct Proof of Dark Matter." Clo's quoted line was that a universe dominated by dark stuff seems preposterous, so they wanted to test whether there were any basic flaws in the thinking, and that these results are direct proof that dark matter exists. Markovich added that this is the most energetic cosmic event, besides the Big Bang, that we know about. One number in the popular accounts is wrong, and it is worth correcting, because it gets repeated constantly. The figure of 4,500 kilometers per second is often given as the speed of the bullet. It is not. It is the speed of the shock front. Springel and Farrar showed in 2007 that the relative velocity of the two dark matter components is only about 3,000 kilometers per second, because the main cluster's own gas is falling toward the bullet at around 1100, and the shock moves faster than the material behind it. The initial infall velocity, back when the two clusters were 3.4 megaparsecs apart, was only about 2000. The energy accounting is worth noting as well. An event of this scale released more energy than anything we know of other than the Big Bang itself, and it produced almost no visible light. Nearly all of it went into heating gas that was already at tens of millions of Kelvin and pushing it around. The most energetic thing in the observable universe since the beginning happened, and to an ordinary eye it would have looked like nothing at all. The bullet cluster is no longer alone. Max J0025.4-1222, nicknamed the baby bullet, shows the same separation at higher redshift. El Gordo, further away still, has been argued to be improbably fast and massive for standard cosmology. And then there is Abel 520, nicknamed the train wreck, which shows the opposite, a mass peak sitting on the gas, nearly devoid of galaxies. A dark core. Nobody has satisfactorily explained it, and it is a genuine outstanding problem rather than a footnote. A number of similar collisions have now been catalogued, and collectively they do more than repeat the result. Because dark matter in these systems shows no sign of slowing down when it passes through itself, the observations put an upper limit on how strongly dark matter particles can interact with each other. Whatever it is not merely invisible. It is very close to non-interacting, even with its own kind, which rules out a considerable range of otherwise reasonable candidates. The argument itself has not closed either. Brownstein and Moffat claimed as early as 2007 that modified gravity could fit this object without dark matter. In 2025 and 2026, Just produced the most detailed mass map of the bullet cluster ever made, and a separate team using the same photometry argued that the lensing in the core region is also consistent with modified gravity, once the baryon budget is expanded to include stellar remnants. That work is contested, but it is being done on new data by people looking carefully. What is not in dispute is the observation. Two objects, each containing something like 100 trillion stars worth of material, collided at thousands of kilometers per second. The part that glows stopped. The part that carries most of the mass kept going. And it kept going not because it missed, but because most of what a galaxy cluster is made of can pass through itself without touching. The next place has been holding a single note for 2.5 billion years. Number 4, the Perseus cluster. The Perseus cluster, catalogued Abell 426, lies about 250 million light-years away and contains around 500 galaxies. It is the brightest galaxy cluster in the X-ray sky. Its central gas runs at roughly 50 million Kelvin. At its heart sits a galaxy called NGC 1275, also known as Perseus A, and inside that galaxy is the supermassive black hole responsible for everything that follows. NGC 1275 sits about 73 megaparsecs from us and is one of the most heavily studied active galaxies in the sky, which is part of why the discovery happened here rather than somewhere else. Perseus is bright. It is relatively close for a rich cluster, and it had already accumulated decades of observation before Chandra arrived. When a telescope with genuinely new capability is pointed at the best characterized object of its type, the things it finds tend to be things that were always present and simply could not be resolved. In 2002, Chandra took a long exposure of the cluster core. On the 9th of September, 2003, NASA announced the result under a headline that was, unusually, meant literally. Chandra hears a black hole for the first time. Andrew Fabian of Cambridge's Institute of Astronomy led the analysis. What the image showed, once the smooth emission was subtracted away, was a set of concentric ripples running outward through the hot gas. Not filaments, not shells of debris. Ripples, alternating regions of slightly higher and slightly lower pressure, propagating outward through a continuous medium. Pressure waves in a medium are sound. That is what sound is. So the team did the obvious thing and calculated the pitch. The note is B flat, 57 octaves below middle C. Chandra's own phrasing was that at a frequency over 1,000,000 billion times deeper than the limits of human hearing, this is the deepest note ever detected from an object in the universe. Each octave downward is a halving of frequency, so 57 octaves below middle C means the frequency has been halved 57 times. The lowest note a human ear can register sits around 20 vibrations per second. This one completes a single cycle in just under 10 million years, a figure usually quoted as 9.6 million. Its wavelength is about 35,000 light-years, and the ripples have been traced out to 50 kiloparsecs from the core. It is worth being clear about what is and is not being claimed here. Nobody has listened to this. No microphone could, and no ear could, and even if one could, a single cycle would take 10 million years to arrive. What Chandra detected was a pattern of alternating pressure in an image. Calling it a note is not a metaphor dressed up for a press release. It is the correct physical description of what a periodic pressure variation in a continuous medium is. But the sound exists as a structure, not as an experience. There is nothing there to hear it. Say that plainly. There is a sound wave whose individual peaks are separated by 35,000 light-years, traveling through a medium that fills a galaxy cluster, and a single oscillation of it takes longer than the entire history of primates. There is a point worth clearing up before going further, because it sounds like a contradiction. Sound requires a medium, and space is famously described as a place where sound cannot travel. That description is accurate for the space between the planets, and for the space between the stars, where the gas is so sparse that a wave cannot organize itself before it dissipates. But the intracluster medium is different in one crucial respect. It is continuous. It is extraordinarily thin, perhaps 100 million times thinner than air, but it is unbroken across millions of light-years, and a wave with a wavelength of 35,000 light-years does not care that the particles are far apart. At that scale, it is a medium, and it carries. The mechanism is not exotic. Jets from the central black hole inflate two enormous bubble-shaped cavities in the surrounding gas. Those cavities behave like pistons, As they expand, they push on the medium around them, and that push propagates outward as a pressure wave. Creating the cavities requires energy equivalent to roughly 100 million supernovae. That energy turns out not to be incidental. It solves a problem that occupied cluster astrophysics for about 2 decades. Here is the problem. The gas at the center of a cluster like Perseus is dense, and dense gas radiates efficiently. Left alone, it should cool. As it cools, it loses pressure support, so it sinks inward, which makes it denser, which makes it cool faster. Run that calculation forward, and the center of the cluster should be collapsing into an enormous, continuous burst of star formation, converting hundreds of solar masses of gas into stars every year. That process is called a cooling flow, and it is what the physics demands. It does not happen. Cluster cores are far quieter than the calculation says they should be. Something is putting heat back in at almost exactly the rate it is being radiated away, and doing so steadily enough that the balance has held for a very long time. The sound waves are a large part of the answer. They carry energy outward from the black hole and dissipate it gradually into the gas as they go, keeping it warm, holding off the collapse. Cavities of this kind have now been found in dozens of clusters, and the energy they carry consistently matches what is needed. But for that mechanism to work in Perseus, the note has had to hold roughly constant for about 2.5 billion years. That is the fact to sit with. This is not an event. It is a condition. A supermassive black hole has been playing the same B-flat continuously into 250 million light-years of gas since before multicellular life appeared on Earth. It was sounding while the atmosphere here was still filling with oxygen. It was sounding through every extinction, every ice age, every ocean. It is sounding now. And the only reason 1 trillion stars have not already formed at the center of that cluster is that nothing has stopped it. The central galaxy has its own peculiarity. NGC 1275 is threaded with filaments of warm hydrogen gas, about 200 light-years wide and up to 20,000 light-years long. Structures that thin and that extended should have been torn apart by turbulence in the surrounding medium long ago. Fabian and colleagues showed in Nature in 2008 that a magnetic field of about 100 microgauss in balance with the surrounding pressure is what holds them together. They are being carried outward in the wake of the rising bubbles, and the magnetic field is keeping them intact along the way. The current chapter belongs to a spacecraft called XRISM, which launched in 2023, carrying an instrument capable of measuring the energy of individual X-ray photons precisely enough to detect gas moving at tens of kilometers per second. It has mapped Perseus more thoroughly than any other cluster, using 4 datasets from 2024 and 5 further pointings in 2025 for 745 kiloseconds of exposure. What it found is a velocity structure with shape to it. The line-of-sight velocity dispersion is about 200 kilometers per second near the center, drops to 80 further out, then rises to 200 again beyond that. Within the innermost 60 kiloparsecs, it stays below 100. An eastern region, coincident with an excess in X-ray brightness, shows about 300, which implies that 7 to 13% of the pressure holding the cluster up is not thermal at all, but turbulent. And there is a dipole pattern of bulk motion, east against west, at 200 to 300 kilometers per second. Its predecessor Hitomi had already found, in 2016, that Perseus was surprisingly calm at its center, before the spacecraft broke apart in orbit weeks into its mission. XRISM has confirmed that calm, and for the first time, separated out what is causing what. The black hole's feedback on one side, and the slower sloshing of a cluster still settling from past mergers on the other. The next entry is falling toward us, and it may have been here before. Number 3. The Smith Cloud. In 1963, a doctoral student at Leiden published a short paper describing a peculiar feature in 21-centimeter radio data taken at Dwingaloo. She published as G.P. Smith. Her name was Gail Beeger. The object has carried her name ever since, and it is one of the few things in this list you could argue is coming to find us. The technique that found it is worth a sentence, because it is the workhorse of everything we know about the cold gas in our galaxy. Neutral hydrogen emits at a wavelength of 21 centimeters, produced by a very rare flip in the relative alignment of the proton and electron in a single atom. Any individual atom does this perhaps once in 10 million years. But hydrogen is so abundant that across a cloud the size of the Smith cloud, the combined signal is easily detectable, and it passes through interstellar dust that would block visible light entirely. Radio astronomers have been mapping the invisible part of the galaxy with it since the 1950s. The Smith cloud sits in Aquila and spans 10 to 15 degrees of sky. If it emitted visible light, it would stretch across roughly 30 times the width of the full moon. It is a cloud of neutral hydrogen, and it is enormous. The Green Bank telescope measurements give it a projected length of about 9,800 light-years and a width of about 3,300. The figures quoted alongside the 2016 Hubble results run slightly differently, at 11,000 light-years long by 2,500 across for the comet-shaped part. Either way, the shape is the thing. A dense head with a trailing tail, which is the signature of something plowing through a thin medium and being stripped from behind as it goes. The comet shape deserves one more note because it is diagnostic rather than decorative. A cloud moving through a galaxy is not moving through nothing. The halo of the Milky Way is filled with extremely thin, extremely hot gas, and anything traveling through it at nearly 300 kilometers per second feels that as a headwind. The head of the cloud is compressed by it. The back is stripped away and drawn out behind. The shape is therefore a record of the direction of travel, visible in a single image, before anyone measures a velocity at all. Its mass is at least 1 million solar masses of hydrogen. It sits about 12.4 kiloparsecs from us, somewhere between 36 and 45,000 light-years, with its leading tip 7.6 kiloparsecs from the galactic center and only 2.9 kiloparsecs below the plane of the galaxy. It is moving at 296 kilometers per second, with a component of 73 kilometers per second directed at the disk. Press coverage usually renders that as nearly 700,000 miles per hour. And it is going to hit. The impact is expected in roughly 27 to 30 million years. It will strike the Perseus arm, the next major spiral arm outward from our own, at an angle of about 45 degrees. That is not a vague expectation. The trajectory is measured, the target region is identified, and the arrival window is known. Objects like this are known collectively as high-velocity clouds, and they have been catalogued since the 1960s. What they are, and where they come from, has been argued over ever since, largely because most of them are too diffuse or too poorly located to pin down. The Smith cloud is the exception. It is close enough, dense enough, and well enough positioned that its distance, its mass, and its full three-dimensional velocity have all been measured directly rather than estimated. That is why it carries so much of the weight of the debate. For decades, the interesting question was not whether it would arrive, but where it came from, and there were two very different possibilities. It might be pristine gas, material left over from the early universe, never processed through a star, falling into the galaxy for the first time. Galaxies need a supply of fresh gas to keep forming stars, and where that supply comes from is a real open question. Or it might be something else entirely. In January of 2016, Andrew Fox of the Space Telescope Science Institute and colleagues settled it, using a technique that is worth describing because it is clever. You cannot easily measure the chemistry of a cloud that produces no visible light of its own. But you can measure what it absorbs. Fox's team identified 3 distant active galactic nuclei whose light happens to pass through the Smith cloud on its way to us, and used the cosmic origin spectrograph on Hubble to take ultraviolet spectra of them. Whatever elements are in the cloud imprint absorption lines on that light. They combined those with green bank radio spectra along the same lines of sight, so they knew exactly how much hydrogen the light had crossed. Sulfur was the gauge. The measured abundance came out at about half the Sun's. That single number closes both alternatives at once. Pristine gas from the early universe would have almost no sulfur at all, because sulfur is made in stars, and there were no stars to make it. Half solar is nowhere near pristine. And it is not the composition of some unrelated dwarf galaxy either. It matches something much closer to home, the Milky Way's own outer disk, at around 40,000 light-years from the center, roughly 15,000 light-years beyond where the Sun sits. So the Smith cloud is Milky Way material. Run the trajectory backward, and it was launched from the outer disk about 70 million years ago, on a 100-million-year arc, and it is now on the way back down. Fox's summary was that the Milky Way is a bubbling, very active place, where gas can be thrown out of one part of the disk and then return back down into another. There is a complication that nobody has resolved, and it is a good one. Nichols and Bland-Hawthorne pointed out in 2009 that the trajectory requires the cloud to have passed through the galactic disk already, at least once. An ordinary cloud of gas, with nothing but its own weight holding it together, would not survive that. Ram pressure and tidal forces would tear it apart on the way through. For it to still be here, intact, with a coherent shape and a coherent velocity, something must be holding it together. Their proposal was a dark matter halo. A subhalo, in the technical language, a clump of dark matter without enough gas or stars ever to have become a proper galaxy. A failed dwarf. J. Lockman at the National Radio Astronomy Observatory keeps a hybrid version alive, noting that the cloud has all the characteristics of a small, infalling, dark matter-dominated galaxy, but that its gas looks like it came from the outer parts of the Milky Way. Both observations can be true if a dark subhalo swept up galactic gas as it passed through. If that reading is right, then the Smith cloud is one of the very few dark matter subhalos we could point a telescope at, because almost every other one would be entirely invisible. Its total mass, in that case, could be 100 times its hydrogen mass. To put 27 million years in some order, that is roughly the span back to the Oligocene, when the first grasslands were spreading and the ancestors of modern apes had not yet appeared. On the timescales this list has been dealing with, it is close to immediate. The impact site is also somewhere we can see clearly from here, which means that when it happens, it will happen in a part of the sky already thoroughly mapped. What happens on arrival is not a catastrophe, and it is worth saying so plainly. This is not an object aimed at Earth, and 27 million years is not a warning. The expected outcome is a burst of star formation where it lands, or possibly a shell of neutral hydrogen blown into the disk. There is enough material there to make about 2 million stars the mass of the Sun. It is simply an event. A large one, arriving on a known schedule, at a known place, involving 1 million solar masses of gas that our own galaxy threw into the sky 70 million years ago, and which has been falling back down ever since. The next place is a piece of the object our galaxy was built out of, and every other piece was destroyed. Number 2. Terzan 5. Agop Terzan found it in 1968, It sits inside the central bulge of the Milky Way, in Sagittarius, about 19,000 light-years from us, and only 1 to 2 kiloparsecs from the galactic center itself, on a short and highly eccentric orbit that carries it in to about 0.8 kiloparsecs and back out to about 2.8. For 40 years it was filed as an ordinary globular cluster. A badly obscured one, but ordinary. The obscuration is the reason it took so long to find out otherwise, and it is worth understanding, because it is the same obstacle that hid Westerlund 1. Looking at the galactic bulge means looking through the entire thickness of the galactic disk, and the dust in that path is heavy and patchy. Add to that the crowding. In the direction of the bulge, stars pile up along the line of sight in such numbers that separating the ones belonging to a particular cluster from the ones simply behind or in front of it is a serious problem in its own right. Terzan 5 was hard to look at, so for a long time nobody looked very hard. In 2009, Francesco Ferraro and colleagues published a paper in Nature that changed what it was. Using an adaptive optics system on the Very Large Telescope, with follow-up spectroscopy at Keck, they measured the cluster's stars carefully enough to build a color magnitude diagram, which is the standard tool for reading a stellar population's age. Adaptive optics is what made the measurement possible, and the principle behind it is worth a moment. The atmosphere above a telescope is turbulent, and that turbulence smears starlight into a blur that limits what any ground-based instrument can resolve. An adaptive optics system measures that distortion hundreds of times a second, using a reference source, and deforms a flexible mirror in real time to cancel it out. The system used here was a multi-conjugate design, which corrects across a wider field than conventional versions. In a field as crowded as the bulge, resolving individual stars cleanly is not a refinement. It is the whole measurement. What they found was that Terzan 5 does not have one population. It has at least two, with different ages and different chemistries. An old population at about 12 billion years, with an iron abundance somewhat below the Sun's. And a young population at about 4.5 billion years, with an iron abundance somewhat above the Sun's. Hubble pinned both ages more precisely in 2016. That combination is not permitted in a globular cluster. A globular cluster forms once. All its stars condense out of a single cloud, within a few million years of each other, out of gas that was thoroughly mixed beforehand. The defining observational property of a globular cluster is that its stars are the same age and the same composition. That is what makes them useful. They are clean samples, and almost everything we know about stellar evolution has been calibrated against them. It is worth dwelling on how much rests on that assumption elsewhere in astronomy, because it explains why the result mattered beyond this one object. Globular clusters are used as calibration standards. If every star in a cluster is the same age and composition, then any difference between them must come from mass alone, and the whole population becomes a controlled experiment in how stars of different masses evolve. Distances, ages, even estimates of the age of the universe itself have been anchored to that logic. So finding an object that looks like a globular cluster, sits in the catalogue as a globular cluster, and turns out to have been enriching itself for 8 billion years, is not a curiosity. It is a warning that the catalogue may contain other things that are not what they are labelled as. Terzan 5 has two populations, separated by 7.5 billion years, and the younger one is richer in iron than the older one, by roughly a factor of 3. That is not a cluster. That is a fossil record of progressive enrichment. Stars formed, lived, exploded, seeded the surrounding gas with the heavy elements they had manufactured, and then, billions of years later, more stars formed out of that enriched gas. For that to happen, the object must have been massive enough to hold onto its own supernova ejector. A supernova throws material outward at thousands of kilometers per second. Anything that cannot retain that material simply loses it, and the enrichment never happens. Terzan 5 kept it. The cluster's mass is usually given as about 2 million solar masses, derived from its light. Later dynamical modeling, based on how its stars move rather than how much they shine, gives values 2 to 3 times lower. That is a real discrepancy, and it has not been reconciled. But even at the low end, this is a heavy object by cluster standards, and the mass is central to the argument, because holding on to supernova ejecta over billions of years is fundamentally a question of how deep the gravitational well is. Ferraro's team proposed that Terzan 5 is not really a cluster at all. It is a bulge fossil fragment, a surviving piece of the massive primordial clumps that merged together to build the galactic bulge in the first place. Ferraro's own phrasing was that for some reason, this peculiar clump of stars formed separately from the bulge and was not destroyed as the bulge itself formed. In June of 2026, at the American Astronomical Society meeting in Pasadena, a team led by Giorgia Zullo at the University of Bologna, with Ferraro as principal investigator and Barbara Lanzoni and Michael Rich among the collaborators, presented JOST results. They combined new near-infrared imaging with archival Hubble data, giving them a 12-year baseline. That baseline let them measure how the stars had moved across the sky in the interval, which finally allowed a clean separation of genuine cluster members from the bulge stars crowding the same line of sight. With the contamination removed, they found up to 4 distinct populations. The 2 known ones refined to 12.5 and 4.7 billion years, plus new ones at 3.8 and 2.5 billion. 4 generations is a different claim from 2. 2 could conceivably be explained by a single external event, a cloud of gas captured from elsewhere, forming one later burst. 4 cannot. 4 means the object sustained its own star formation, on and off, across most of the history of the universe. Terzan 5 has one further distinction, and it comes from a completely different technique. It is the most pulsar-rich globular cluster known. 39 was the standard count through the early 2020s. A survey using the Meerkat array in South Africa added 10 more in 2024 from only 4 hours of observation, bringing the total with detected radio pulsations to 49. Pulsar timing works at radio wavelengths, which pass straight through the dust that made the optical work so hard. While astronomers were struggling to photograph this object, radio astronomers had been listening to it without difficulty for years. Among those pulsars is one catalogued PSR J1748-2446 AD, and it holds a record. It is the fastest spinning pulsar known, 716 rotations every second. It was found by Jason Hessels and colleagues in 2006, and it displaced a record that had stood since 1982. 716 times a second. That is a neutron star roughly 20 kilometers across, containing more mass than the Sun, completing a full rotation in 1.396 milliseconds. Its equator is moving at a substantial fraction of the speed of light. It is close enough to the theoretical limit at which such an object would begin to break apart that its existence constrains the physics of matter at nuclear density. Now step back and consider what this object is. The Milky Way's bulge was assembled in the first billion years or so out of a small number of massive clumps that fell together and merged. That process is violent. The clumps are disrupted, torn apart, and stirred into the general population of the bulge, where their stars remain, but their identity as separate objects is gone forever. Essentially, all of them were destroyed. That is what building a galaxy means. This one was not destroyed. it is still bound. It is still there, 19,000 light-years away, behind enough dust that it took 4 decades to recognize, holding stars that formed 12.5 billion years ago, alongside stars that formed after the Sun did. It survived the construction of the thing it was supposed to become part of, and it has been sitting in the middle of that thing ever since, intact. There is a particular quality to the older stars there that is worth naming. They formed 12.5 billion years ago in an object that was then one of several massive clumps orbiting in a young galaxy that did not yet have a disk or spiral arms or a name. Those stars watched the rest of their siblings get pulled apart. They are still burning, still bound to the same fragment they formed in, and the fragment is still moving on its own orbit, in and out of the galactic center, every few tens of millions of years, as it has done for essentially the whole history of the Milky Way. Lila 1 is the only other object of this kind currently known. Ferraro's team plans to screen 40 to 50 more bulge clusters for the same signature, which leaves one place, and it is the one that has been overhead the whole time. Number 1. The Radcliffe Wave. On the 7th of January 2020, a paper appeared in Nature announcing a structure in our own neighborhood that nobody had known was there. The team was João Alves of the University of Vienna, at the time a fellow at the Harvard Radcliffe Institute, from which the structure takes its name, Catherine Zucker, then a doctoral student at Harvard, and Alyssa Goodman, also at Harvard. Their method was to combine astrometry from the Gaia spacecraft with a technique called three-dimensional dust mapping. That technique is the key to everything that follows, so it is worth explaining. Interstellar dust reddens starlight in a way that depends on how much dust the light has crossed. If you know a star's distance and you know how reddened its light is, you can work out how much dust lies between you and it. Do that for enough stars at enough different distances, and you can build a genuine three-dimensional model of where the gas and dust in the galaxy actually sit. Not a picture of the sky, a model of the volume. Gaia is what made that possible. It has measured positions and motions for nearly 2 billion stars, which means that for the first time, astronomers had reliable distances in enough quantity to fill in the third dimension. What Alves, Zucker, and Goodman found in that volume is a filament of star-forming gas about 9,000 light-years long and 400 light-years wide, containing more than 3 million solar masses of material. At its closest, it comes within about 500 light-years of the Sun. And it is not straight. It is sinusoidal. A wave with a wavelength of about 2 kiloparsecs and an amplitude of around 160 parsecs, damped along its length. Now, the part that reframes it. The regions that make up this filament are not obscure objects in a catalogue. They are the ones every amateur astronomer already knows by name. Orion, Taurus, Perseus, Cepheus, Canis Major, Cygnus X, the North America Nebula complex. Those are the nearest star-forming regions to Earth. They are the objects in every beginner's guide, the ones that appear in every wide-field photograph of the winter sky. And for about 150 years they had been understood as a ring. The Gould Belt was described in the 1870s, named for Benjamin Gould, who noticed that the bright young stars near the Sun appeared to lie along a great circle tilted relative to the plane of the Milky Way. It became a standard feature of the textbooks. Generations of astronomers were taught it. A ring of star formation, with the Sun inside it. It does not exist. The Gould Belt was an illusion produced by projection. Take a long, undulating, three-dimensional filament, look at it from a point near one end without good distance information, and flatten it onto the sky, and it can perfectly well look like a ring. For a century and a half, we had the shape wrong, not because the objects were hidden or faint or far away, but because we could not measure how far away they were accurately enough to tell. The Radcliffe wave appears to be the gas spine of the local arm, the dense backbone of the nearest spiral arm of our own galaxy. And we are next to it. That was 2020. In February of 2024, a second Nature paper made it considerably stranger. Ralph Konietzka, with Goodman, Zucker, Alves and colleagues, used the three-dimensional motions of young star clusters born out of the wave's clouds to trace the motion of the gas that made them. Star clusters inherit the velocity of the material they condense from, so they can be used as tracers of what the gas was doing. The structure is not a static shape. It is oscillating. The whole 9,000 light-years of it moves as a traveling wave, with a maximum vertical velocity of about 14 kilometers per second, while the structure as a whole drifts outward from the galactic center at about 5 kilometers per second, roughly 11,000 miles per hour. Konietzka's analogy was a stadium wave, similar to how fans in a stadium are pulled back down into their seats by gravity. The Radcliffe wave oscillates because of the gravity of the Milky Way. The paper also computed the dark matter contribution explicitly and found that none is required. The gravity of ordinary matter alone drives the motion. This is a 9,000 light-year structure, immediately next door, in motion, sustained by nothing more exotic than the mass that is already visible in it. What set the wave waving is an open question, and the candidates are worth hearing because they are very different in character. Goodman's own framing of it is to ask what caused the displacement giving rise to the waving, and whether it happens all over the galaxy. The first candidate is internal, a series of clustered supernova explosions going off in the same region over a few million years, pushing the gas out of the plane and letting galactic gravity pull it back. The second is external, a dwarf satellite galaxy passing through the Milky Way and ringing the disk like a struck surface. Several such galaxies are known to have done exactly that, and the disk carries other evidence of having been disturbed. The consequences of the second option are larger than they sound. Because the Radcliffe wave is the backbone of the nearest spiral arm, if this arm is oscillating, there is no particular reason to think other arms are not. Spiral arms may not be the static structures they are drawn as. They may be waving too, and we would not know, because we cannot get outside our own galaxy to look, and the technique that revealed this one only works within a few thousand light-years of the Sun. There is also a dissenting result, and honesty requires including it. Chernyshov, Peake and colleagues argued in 2024 that differential galactic rotation, the fact that material closer to the center orbits faster than material further out, should shear a structure of this length apart faster than it can complete a single oscillation. On that reading, the wave is a transient feature rather than a standing one, caught during a brief window in which it happens to be coherent. That would make it less a permanent property of the arm and more an accident of timing, which is its own kind of strange. And then there is the part that concerns us directly. Marconi and colleagues published work in 2025 concluding that the solar system crossed the Radcliffe wave in the Orion region, most likely between about 15 and 12 million years ago. The commonly quoted figure is 13 million. We did not pass near it. We went through it. That crossing coincides with the Middle Miocene climate transition, a period of substantial global cooling on Earth and the expansion of the Antarctic ice sheet. The authors raise the coincidence and explicitly decline to claim any causal connection, which is the correct posture. Correlations of that kind are easy to find and difficult to justify, and one alignment of dates is not evidence of a mechanism. But the crossing itself is not in dispute. There is a structure containing 3 million solar masses of gas and dust, and the Sun spent time inside it, well after the ancestors of modern apes had appeared. There is a related structure worth mentioning alongside it, without overstating the connection. The solar system currently sits inside the local bubble, a cavity in the interstellar medium carved out by supernovae, and the stars that produced those supernovae came from these same nearby star-forming complexes. Zucker and colleagues showed in 2022 that star formation in our immediate neighborhood is driven by the expansion of that bubble. The two facts are adjacent rather than causally linked, and no published work directly connects the sun's crossing of the wave to the bubble's formation. But they are describing the same small region of the galaxy and the same handful of clouds, from two directions. So go outside tonight and find Orion. It is not difficult. 3 stars in a row, the most recognizable pattern in the sky, and hanging below them, the faint smudge that is the Orion Nebula, 1,300 light-years away, visible without any instrument at all. People have been looking at it and naming it for as long as there have been people. It is on cave walls. It is in the oldest star catalogues we have. Now hold the rest of it in your head at the same time. That nebula is not a single object hanging alone in the dark. It is one bead on a string 9,000 light-years long, and the string runs off in both directions past the limits of what you can see. Taurus is on it. Perseus is on it. Cygnus, on the other side of the sky, in a different season, is on the same structure. Every nearby star-forming region you have ever been shown through a telescope is part of one connected thing. And the string is moving, not drifting, waving, the whole enormous length of it rising and falling under the galaxy's own gravity at 14 kilometers a second, in a motion that will take tens of millions of years to complete a single cycle. The sky above you does not change while you stand there. The stars are where they were. Orion is exactly where it has always been. Nothing about the view is different from the view your grandparents had, or the view someone had 4,000 years ago. What changed is what it is understood to be. And it changed in 2020. That is why this is the top of the list. Everything else on it is remote, or hostile, or exotic. Mercury's hollows are dissolving on a planet nobody will stand on. The lunar cold traps are colder than Pluto, but they are 4 days away, and we are going. The bullet cluster is 3.4 billion light-years off. Terzan 5 is buried behind the bulge. Those are places you have to travel to, physically or conceptually, to be unsettled by. The Radcliffe wave required no traveling at all. It has been directly overhead for the entire history of the species. It contains the most photographed objects in the night sky. The sun has already been through it. And for 150 years we looked straight at it and described it as a ring, because measuring the distance to a star is genuinely hard, and until a spacecraft measured 2 billion of them, nobody could see the shape. That is the thing worth carrying away from 20 places that actually exist. Not that the universe is hostile, though most of it is. Not that it is large, though it is. But that the difficulty was never that these things were hiding. Mercury's hollows were photographed in 1974 and set aside. The plates of OJ-287 sat in cabinets for 90 years. Terzan 5 was catalogued in 1968 and misfiled for 4 decades. The red rectangle has been emitting light nobody can identify since long before anyone built an instrument to catch it. None of them were concealed. We simply had not yet built the thing that would let us look properly, and then somebody did, and there it was, exactly where it had always been. The wave is still moving tonight. It will keep moving long after every question raised in the last 3 hours has been either answered or abandoned. And the next time you are outside and you happen to find those 3 stars in a row, you will know that they are riding on something enormous and slow, and that it is carrying them, and that it once carried us. Sleep well and good night.